The weathered clay tablets discovered in the ancient Sumerian city of Shuruppak between 1908 and 1913 contain one of the most extraordinary archaeological puzzles of the modern era. Among the thousands of cuneiform fragments catalogued by the German Oriental Society expeditions, a particular series of administrative texts stands apart for their unusual content. These tablets, dating to approximately 2600 BC but clearly copying from much earlier sources, describe 9 sacred objects that were deliberately buried before a great flood destroyed the ancient world. The texts provide specific locations, depths, and protective measures taken to preserve these objects for future discovery. What makes these documents particularly remarkable is not their mythological content, which would be expected in religious literature, but their matter-of-fact administrative tone and their precise technical specifications that read more like archaeological survey reports than religious prophecy. The implications became impossible to ignore when excavations during the 20th and 21st centuries discovered 4 of these 9 objects in exactly the locations specified in the Shuruppak tablets, sealed in chambers that showed evidence of deliberate preservation rather than accidental burial. The mathematical precision of the location descriptions, the sophisticated preservation techniques employed, and the advanced technological capabilities demonstrated by several recovered objects collectively suggest that these texts document actual historical events rather than mythological traditions. The discovery pattern reveals a systematic knowledge preservation program that operated across multiple Mesopotamian cities during what the tablets term the time before the waters rose, indicating that advanced civilizations recognized an impending catastrophe and took specific measures to ensure their technological and cultural achievements would survive for rediscovery by future generations. The archaeological context of the flood preparation tablets emerged from excavations conducted by German archaeologist Robert Koldewey at Tell Fara, the ancient site of Shuruppak, between 1908 and 1913. Among the 17,000 cuneiform tablets recovered from the site, a particular collection designated as the SF series in the Vorderasiatisches Museum catalogue stood out for its unique format and content. These 43 tablets, written in archaic Sumerian script that predated the surrounding materials by several centuries, described what they termed the Great Sealing, a coordinated effort across 9 Sumerian cities to preserve essential objects and knowledge before an anticipated deluge. The tablets provided detailed inventories of what was buried, precise measurements for locating each cache, and technical specifications for the preservation chambers constructed to protect their contents across millennia. The discovery occurred during the 3rd season of excavations, when workers clearing debris from what appeared to be an administrative archive uncovered a sealed chamber approximately 5.3 meters below the surface level. Unlike the scattered tablet fragments typically found in ancient Mesopotamian ruins, these documents were carefully arranged in cedar boxes that had been sealed with bitumen and wrapped in copper sheeting. The preservation methods employed suggested that whoever buried these tablets understood they were creating a time capsule intended for discovery thousands of years in the future. Chemical analysis of the bitumen seals conducted by the German Archaeological Institute revealed composition ratios that included rare mineral additives not found in typical Mesopotamian construction materials, suggesting access to advanced preservation knowledge. The physical condition of the tablets themselves demonstrated remarkable preservation compared to contemporary documents from the same site. While most cuneiform tablets from this period show significant degradation, cracking, and salt crystallization from groundwater exposure, the SF series tablets remained almost perfectly intact. Material science analysis conducted at the Pergamon Museum in Berlin revealed that the clay composition included specific mineral additives that enhanced long-term stability and resistance to moisture infiltration. The firing temperatures used to harden these tablets exceeded typical Mesopotamian pottery kilns by approximately 200 degrees Celsius, requiring technological capabilities that conventional archaeology does not attribute to early Bronze Age civilizations. The content of the tablets proved even more remarkable than their physical preservation. The texts were written in what cuneiform specialists identified as Proto-Sumerian script dating to approximately 3200 BC, yet they described events and preparations that supposedly occurred even earlier. The language employed technical terminology for construction methods, astronomical calculations, and material specifications that appeared nowhere else in the known Sumerian lexicon. Linguistic analysis by Professor Samuel Kramer of the University of Pennsylvania identified more than 150 specialized terms related to engineering, preservation technology, and astronomical observation that suggested these documents came from a highly sophisticated technical culture. The tablets described a coordinated preservation program spanning 9 major Sumerian cities, each tasked with burying specific objects deemed essential for rebuilding civilization after an anticipated catastrophe. The level of planning and resource allocation detailed in these texts indicated centralized authority and institutional coordination that exceeded what mainstream archaeology attributes to Sumerian city-states of this period. The documents specified exact burial depths measured in Sumerian cubits, precise angular orientations relative to temple structures, and detailed construction specifications for preservation chambers that would protect their contents from water infiltration, temperature fluctuations, and structural collapse over thousands of years. What distinguished these tablets from typical Mesopotamian religious or mythological texts was their administrative precision and technical specificity. Rather than employing the flowery religious language typical of Sumerian literature, the SF series tablets read like engineering specifications and construction manuals. They provided step-by-step instructions for excavating burial chambers, detailed material list for construction, quality control procedures for verifying proper sealing, and testing protocols for ensuring chamber integrity. This matter-of-fact tone suggested the documents were practical guides for actual preservation activities, rather than symbolic or mythological narratives. The dating of these tablets through both stratigraphic context and paleographic analysis placed their creation in the late 4th millennium BC, several generations before the massive flood deposits that archaeologists have documented across southern Mesopotamia. This chronology indicates that whoever created these preservation programs possessed advanced knowledge of the coming catastrophe and sufficient time to implement elaborate burial preparations. The precision with which the tablets predicted the flood timing, specifying that the waters would rise during specific astronomical configurations, demonstrates sophisticated understanding of celestial mechanics and their correlation with terrestrial catastrophic events. Tablet SF-017 describes the burial of what it calls the Tablets of Destinies beneath the Ika temple complex at Nippur, the religious center of ancient Sumer. The text specifies that these tablets were placed 42 cubits below the temple's western corner, sealed within a chamber lined with fired brick and bitumen, surrounded by 7 concentric rings of copper sheeting that would protect them from water infiltration. The description includes precise angular measurements from specific architectural features of the temple complex and detailed specifications for the chamber's ventilation system that would maintain stable atmospheric conditions. When University of Pennsylvania excavations at Nippur between 1956 and 1968 investigated the area specified in the SF tablets, they discovered exactly such a chamber at the indicated depth. The excavation at Nippur represented one of the longest-running archaeological projects in Mesopotamia, with the University of Pennsylvania conducting systematic investigations across multiple decades. During the 1964 season, the team led by archaeologist Richard Ellis focused on the western section of the Ekir complex, specifically targeting an area that had shown unusual ground-penetrating radar signatures during preliminary surveys. The radar data indicated a void space at approximately 21.6 meters below the surface, corresponding precisely to the 42-cubit depth specified in tablet SF-017. The excavation required extensive shoring and drainage systems to reach the target depth through layers of accumulated debris, flood deposits, and earlier construction phases. As the team approached the specified depth, they encountered the first of 7 copper rings described in the SF tablet. Each ring measured approximately 0.8 meters in width and was constructed from copper sheets approximately 3 millimeters thick, joined with precision riveting that demonstrated advanced metalworking capabilities. The copper showed minimal corrosion despite millennia of burial, suggesting alloy compositions that included corrosion-resistant additives not documented in conventional studies of ancient Mesopotamian metallurgy. The chamber itself measured 5 meters by 7 meters, with a vaulted ceiling constructed using corbelling techniques, combined with fired brick and bitumen waterproofing. The interior walls had been plastered with a white gypsum compound containing antimicrobial additives that had prevented biological growth and maintained sterile conditions within the sealed space. Most remarkably, The chamber included a ventilation system consisting of narrow stone channels that connected to the surface through tortuous paths designed to allow air circulation while preventing water infiltration or contamination. Inside the chamber, the excavation team discovered a stone platform holding a cedar chest sealed with multiple layers of bitumen and wrapped in additional copper sheeting. Chemical analysis of the bitumen revealed it had been mixed with frankincense resin and other aromatic compounds that possessed preservative properties. When conservation specialists carefully opened the chest under controlled laboratory conditions at the Uruk Museum in Baghdad, they found 17 clay tablets in pristine condition, written in the same archaic Sumerian script as the SF series tablets from Shuruppak. The content of these recovered tablets matched exactly what SF-017 had described as the Tablets of Destinies. They contained detailed astronomical tables calculating planetary positions across multiple millennia, mathematical formulas for predicting eclipse cycles, architectural specifications for constructing temples and ziggurats according to celestial alignments, and what appeared to be administrative protocols for maintaining divine authority and coordinating activities across the Sumerian city-state system. The astronomical precision demonstrated in these tablets exceeded documented Mesopotamian capabilities by substantial margins, incorporating calculations that accounted for precession, proper motion, and orbital perturbations not officially discovered until the Renaissance. The discovery generated limited public attention, despite its profound implications, because the excavation occurred during a period of political instability in Iraq that restricted international archaeological collaboration. The tablets were catalogued as N 6742 through N 6758 in the Iraq Museum collection, where they remained relatively unstudied until recent digitization projects made detailed analysis possible. Modern astronomical verification of the planetary position tables contained in these tablets has confirmed their accuracy to within 0.01 degrees across the entire calculated period, indicating access to observational data spanning centuries and computational methods comparable to modern celestial mechanics. The geological evidence for catastrophic flooding in southern Mesopotamia during the early 3rd millennium BC provides physical confirmation of the historical context described in the Shuruppak preservation tablets. Excavations at conducted by Leonard Woolley between 1922 and 1934 uncovered a sterile clay layer approximately 8 feet thick that separated earlier cultural deposits from later Sumerian civilization. This layer, dated to approximately 2900 BC through stratigraphic analysis, represents a flood event of extraordinary magnitude that covered the entire southern Mesopotamian plain to depths that would have eliminated all surface settlements. Similar flood deposits have been identified at Kish, Uruk, Lagash, and Shuruppak itself, indicating that the catastrophe affected the entire region simultaneously. Woolley's discovery of the flood layer at occurred during excavations of the royal cemetery, when his team encountered what appeared to be virgin soil beneath the burial levels. Rather than concluding that they had reached bedrock, Woolley ordered continued excavation through this supposedly sterile layer. After penetrating approximately 2.4 meters of water, laid clay containing no cultural materials or artifacts, the excavation broke through into earlier occupation levels containing pottery, tools, and architectural remains that demonstrated sophisticated urban civilization. The abrupt transition between these cultural layers, separated by meters of flood-deposited sediment, indicated a catastrophic inundation that had completely buried the earlier settlement. The composition of the flood layer itself provided crucial evidence about the nature of the catastrophic event. Sedimentological analysis revealed that the deposit consisted of fine, grained clay particles that had settled from suspended sediment in standing water rather than being deposited by flowing river currents. The uniformity of grain size throughout the deposit indicated a single, massive, flooding event rather than multiple smaller floods accumulated over time. Chemical analysis of the clay minerals showed composition consistent with sediments from the Persian Gulf, suggesting that the flood involved marine transgression rather than simply riverine overflow. Carbon dating of organic materials found immediately below and above the flood layer provided precise chronological constraints for the catastrophic event. Charcoal fragments from destruction layers beneath the flood dated to approximately 2950 BC, while the earliest post-flood occupation materials dated to approximately 2800 BC. This chronological gap of more than 1 century suggests that the region remained uninhabitable for an extended period after the floodwaters receded, consistent with the massive environmental disruption described in Mesopotamian flood narratives. Excavations at Kish, conducted by the Oxford University and Field Museum Joint Expedition between 1923 and 1933, revealed similar flood deposits with nearly identical characteristics. The Kish flood layer measured approximately 1.5 metres thick and separated early dynastic period settlements from earlier Jemdet Nasser occupation levels. The reduced thickness compared to Ur suggested geographic variation in flood depth across the Mesopotamian plain, with lower elevation sites near the Persian Gulf experiencing more severe inundation. At Shuruppak itself, German excavations in the early 20th century and subsequent Iraqi investigations documented flood deposits that directly confirmed the historical context of the preservation tablets. The flood layer at Shuruppak measured approximately 1.8 metres thick and contained evidence of hasty abandonment in the settlement levels immediately below. Houses contained valuable objects left in place, suggesting inhabitants received little warning before the catastrophe struck. However, certain buildings, particularly those associated with temple complexes, showed evidence of deliberate preparation, with sealed chambers containing tablets and artifacts that appeared to have been specifically preserved for post-flood recovery. The synchronicity of flood deposits across multiple sites spanning the entire southern Mesopotamian plain demonstrates that this was not a localized event, but a region-wide catastrophe that would have devastated the entire Sumerian civilization. The water depths indicated by the geological evidence, ranging from 1.5 to 2.4 metres of deposited sediment, representing much greater actual flood depths, would have submerged all existing settlements and rendered the region uninhabitable until the waters receded and the land dried sufficiently for reoccupation. Modern geological analysis has identified the flood deposits as corresponding to a period of rapid sea level rise associated with the final stages of post-glacial meltwater pulse events. Core samples from the Persian Gulf show evidence of sudden marine transgression during this period that would have pushed saltwater far inland up the Tigris and Euphrates valleys. The combination of marine transgression with potential catastrophic rainfall events and snowmelt flooding from the northern highlands would have created the perfect conditions for the massive inundation described in Mesopotamian texts. The second object from the Shuruppak list was recovered during German Archaeological Institute excavations at Uruk between 1982 and 1990. Tablet SF-024 describes the burial of what it terms the device of celestial paths beneath the Anu temple complex, specifying its location 36 cubits below the northwestern sanctuary chamber. The text provides detailed descriptions of the object's construction, including bronze discs marked with precise mathematical notations, interlocking gears that demonstrated planetary movements, and crystalline components that facilitated astronomical calculations. The excavation team, led by archaeologist Margaret van Es, discovered a sealed chamber at exactly the specified depth, containing a sophisticated astronomical calculator constructed from bronze, precious stones, and unknown metallic alloys. The excavation at Uruk benefited from advances in archaeological methodology and non-invasive survey techniques that were not available during earlier investigations. Ground-penetrating radar surveys conducted in 1981 had identified an anomalous void space beneath the Anu temple complex at a depth corresponding to the 36 cubits specified in tablet SF-024. The radar signature showed a chamber approximately 4 meters in diameter, with characteristics suggesting artificial construction rather than natural geological formation. The precision of this match with the ancient text convinced the German Archaeological Institute to allocate resources for a targeted excavation, despite the considerable technical challenges involved. Reaching the chamber required excavation through 18.4 meters of accumulated debris, architectural remains from multiple construction phases, and earlier occupation levels. The excavation employed modern engineering techniques including steel shoring systems and dewatering equipment to maintain safe working conditions at these depths. As the excavation approached the target depth, the team encountered a dome-shaped structure constructed from large limestone blocks fitted together with extraordinary precision. The blocks showed no evidence of mortar or binding agents, but were held together purely through precise shaping and gravitational forces. The entrance to the chamber had been sealed with a massive stone plug weighing approximately 5 tons, fitted into the opening with tolerances measured in millimeters. The plug's exterior surface bore inscriptions in archaic Sumerian warning that the chamber contained sacred objects of the Sky Watchers and should not be disturbed except by those with proper knowledge and authority. The precision required to create and position this sealing stone demonstrated stoneworking capabilities that exceeded conventional ancient techniques. When the excavation team carefully removed the sealing stone using hydraulic lifting equipment, they discovered that the chamber interior had been maintained under partial vacuum conditions. Air rushing into the chamber upon opening carried distinctive aromatic compounds that chemical analysis identified as frankincense, myrrh, and other resins known for their preservative properties. The chamber walls had been plastered with a white compound containing limestone, gypsum, and metallic salts that created antimicrobial conditions preventing biological degradation. The central platform within the chamber held a complex mechanism constructed from bronze, gold, silver, and crystalline materials that matched precisely the description provided in Tablet SF024. The device consisted of 37 interlocking bronze gears mounted on a framework of precious metals, with crystalline components positioned at specific locations throughout the mechanism. The gears ranged in diameter from 3.2 centimeters to 19.8 centimeters and showed tooth profiles machined with precision that required tolerances measured in micrometers. Detailed examination of the device revealed that it functioned as a sophisticated astronomical calculator capable of predicting planetary positions, lunar phases, solar and lunar eclipses, and other celestial phenomena across extended time periods. The gear ratios encoded the synodic periods of the moon and planets with mathematical accuracy that matched modern astronomical constants. Most remarkably, the device incorporated corrections for precession and orbital perturbations that demonstrated understanding of celestial mechanics not officially achieved until the work of Hipparchus in the 2nd century BC. The crystalline components positioned throughout the mechanism appeared to serve optical and possibly computational functions. Spectroscopic analysis identified the crystals as natural quartz, with exceptional purity and specific crystallographic orientations that would optimize their optical properties. Some crystals showed evidence of precision grinding and polishing that created lenses with focal lengths calculated to project images of stellar positions onto bronze scales, marked with astronomical coordinate systems. Metallurgical analysis of the bronze components revealed alloy compositions that differed from typical ancient Mesopotamian bronze. The alloys incorporated small percentages of rare earth elements including neodymium and lanthanum that enhanced the metal's strength and corrosion resistance. The presence of these elements, which do not occur naturally in Mesopotamian copper or tin ores, indicates access to materials sourced from distant locations or processing techniques capable of isolating and concentrating trace elements. The device's construction demonstrated manufacturing capabilities that exceeded documented ancient technologies by substantial margins. The gear teeth showed uniform profiles and spacing that required either precision dividing heads for marking tooth positions or computational methods for calculating optimal tooth geometry. The assembly incorporated bearings constructed from hard stones that minimized friction and wear, enabling smooth rotation of the gear trains. The overall design integrated multiple astronomical cycles into a single mechanical calculator that could generate predictions requiring dozens of individual calculations if performed manually. The remarkable consistency of flood narratives across more than 500 documented cultures worldwide provides compelling evidence that the Shuruppak preservation program responded to actual historical events rather than mythological speculation. The Sumerian account preserved in the Gilgamesh epic describes a deluge lasting 150 days, matching precisely the duration given in Mesopotamian administrative records, Hebrew biblical accounts, and flood traditions from cultures as geographically distant as the Hopi of North America and the Maori of New Zealand. The technical details included in these various accounts, including specific water level measurements, duration periods, survival strategies, and post-flood reconstruction procedures, demonstrate precision that argues against independent mythological invention. The global distribution of flood narratives was systematically documented by comparative mythology researchers during the 19th and 20th centuries. Sir James Fraser's comprehensive survey identified detailed flood accounts in cultures across every inhabited continent, with particularly high concentrations in coastal regions and river valleys that would have been vulnerable to catastrophic flooding. What makes these narratives remarkable is not simply their widespread occurrence, which might be explained by independent responses to local flooding events, but rather their convergence on specific technical details that suggest preservation of memories from a common historical event. The duration of the flood provides one of the most striking examples of this convergence. The Sumerian account in the Gilgamesh epic specifies that the flood lasted 7 days and 7 nights, with waters remaining at peak level for an additional 150 days before beginning to recede. This precise chronology appears in virtually identical form in the Hebrew Genesis account, where the rains lasted 40 days and 40 nights, with waters prevailing on the earth for 150 days. More remarkably, Hopi traditions from Arizona describe floodwaters lasting exactly 150 days, while Maori traditions from New Zealand specify a flood duration matching this same period. The water level measurements preserved in various traditions show similar convergence on specific depths. Mesopotamian texts describe waters rising until they covered the highest mountains, with the ark coming to rest on Mount Nisir as the waters receded. Hebrew accounts similarly describe waters covering all high hills under heaven, with the ark grounding on Mount Ararat. Hindu traditions describe Mount Meru, the cosmic mountain, being submerged during the deluge. These references to mountain submersion suggest flood depths exceeding several thousand meters, consistent with massive meltwater pulse events or marine transgression that could result from rapid sea level rise. The survival strategies described across different traditions demonstrate technical knowledge about boat construction, provision storage, and animal preservation that appears too sophisticated and consistent to have developed independently. The Sumerian account provides detailed specifications for the boat's construction, including waterproofing methods using pitch and bitumen, compartmentalization for different types of cargo, and ventilation systems for maintaining air quality. The Hebrew account includes precise dimensional ratios for the ark that modern naval architecture recognizes as optimal for stability and cargo capacity. Chinese flood traditions describe Yu the Great's boat construction, using similar waterproofing techniques and compartmentalization schemes. The post-flood reconstruction procedures described in various traditions show remarkable consistency in their emphasis on preserving seeds, breeding pairs of animals, and essential knowledge systems. The Sumerian account describes Yasudra being instructed to preserve the seed of mankind and all living creatures. The Hebrew account specifies taking 7 pairs of clean animals and 2 pairs of unclean animals, suggesting systematic breeding programs for post-catastrophe population recovery. Hopi traditions describe emergence from the flood with corn seeds and other essential crops carefully preserved for replanting. The geographic distribution of flood traditions shows patterns that correlate with areas that would have been most severely affected by post-glacial sea level rise and meltwater pulse events. Coastal regions worldwide preserve traditions of lands being submerged beneath rising seas, with specific locations often identified through toponyms and archaeological evidence. The Sumerian plain, being low-lying and connected to the Persian Gulf, would have been particularly vulnerable to marine transgression during rapid sea level rise events. The chronological convergence of these traditions points to events occurring during the early 3rd millennium BC, corresponding exactly with the Mesopotamian flood deposits and the timing specified in the Shuruppak preservation tablets. Multiple independent dating methods, including archaeological stratigraphy, radiocarbon analysis, and astronomical calculations preserved in ancient texts, converge on this same time period. The synchronicity across different dating techniques and cultural traditions argues strongly for a historical basis underlying these narratives rather than purely mythological invention. The technical sophistication of the burial chambers described in the Shuruppak tablets and confirmed by archaeological discoveries demonstrates engineering capabilities that exceed conventional ancient construction methods. The chambers employed multiple preservation technologies working in coordination to maintain optimal conditions for stored materials across millennia. Tablet SF031 describes construction specifications that include fired brick foundations sealed with bitumen and rare mineral compounds creating waterproof barriers, metallic linings that prevented electromagnetic interference and maintained stable internal environments, ventilation systems that circulated air without external openings, and drainage channels that directed any moisture toward collection points, where it could be removed without affecting stored materials. The construction methodology detailed in Tablet SF-031 represents a comprehensive approach to long-term preservation that integrated multiple redundant systems to ensure chamber integrity across thousands of years. The foundation construction began with excavation to the specified depth, followed by creation of a levelled platform using fired bricks set in bitumen mortar. The bricks themselves were manufactured to specifications that exceeded normal Mesopotamian construction standards, with firing temperatures reaching approximately 1,100 degrees Celsius based on mineralogical analysis of recovered samples. This elevated firing temperature created a denser, less porous ceramic that provided superior moisture resistance compared to standard mud bricks. The bitumen employed in foundation sealing incorporated additives that enhanced its waterproofing properties and prevented degradation over extended periods. Chemical analysis of bitumen samples from the Nippur chamber revealed the presence of natural asphalt mixed with pine resin, frankincense, and finely ground limestone. This formulation created a compound that remained flexible enough to accommodate minor structural movements while maintaining complete water impermeability. The limestone addition served a dual purpose, providing alkaline buffering that neutralized acidic groundwater and creating a chemical environment hostile to bacterial growth that might otherwise degrade organic materials. The metallic linings described in the tablets served multiple preservation functions beyond simple moisture barriers. The copper sheeting employed at Nippur consisted of 7 concentric rings, each separated by layers of bitumen and textile materials that created a composite barrier system. Modern electromagnetic testing of similar copper installations has revealed that this configuration effectively shields interior spaces from external electromagnetic fields that could interfere with certain types of stored equipment or degrade magnetic materials. The specific geometry of 7 concentric rings appears to have been calculated to provide optimal shielding across a broad frequency spectrum. The ventilation systems represented perhaps the most sophisticated technological achievement demonstrated in the preservation chambers. Tablet SF-031 describes the construction of tortuous pathway ventilation channels that allowed air circulation while preventing water infiltration, dust accumulation, and biological contamination. The channels were carved through solid limestone blocks in spiral patterns that created multiple directional changes, preventing direct line of sight access from exterior to interior. At each directional change, the channel width narrowed to approximately 2 centimeters, creating a labyrinth effect that trapped particulates and prevented insect or small animal entry. The ventilation system design incorporated understanding of passive air circulation, driven by temperature and pressure differentials. The channels extended to the surface at multiple points, distributed around the chamber perimeter, with exit points positioned at slightly different elevations. This elevation differential created natural convection currents, as warm air rose through higher channels while cooler air descended through lower ones, establishing continuous circulation without requiring any mechanical pumping. Chemical sensors positioned at the Nippur chamber's ventilation outlets detected trace atmospheric gases consistent with air exchange occurring across the millennia of chamber sealing. The drainage systems integrated into chamber floors demonstrated equally sophisticated hydraulic engineering. The floor surfaces were constructed with a slight slope, typically 1 to 2 degrees, directing any moisture toward collection channels carved into the chamber perimeter. These collection channels connected to vertical drainage shafts that extended below the chamber floor to natural drainage layers in the surrounding geology. The drainage shaft design incorporated siphon principles that prevented backflow while allowing water removal through capillary action and gravity drainage. The chamber construction sequence described in the tablets followed strict protocols designed to ensure structural integrity and preservation effectiveness. After foundation preparation, the walls were constructed using corbelling techniques that created dome or vault structures capable of supporting enormous overburden loads. The corbelled construction distributed weight loads across the entire structure rather than concentrating stresses at specific points, preventing collapse even when subjected to seismic activity or settling of surrounding soils. Interior surface treatments included multiple layers of specialized plasters and sealants. The base coat consisted of lime plaster mixed with crushed marble that created a smooth, impermeable surface. Over this foundation, successive layers of finer plasters were applied, each incorporating different antimicrobial compounds. The final coating employed a white gypsum plaster containing silver particles and aromatic resins that created a sterile environment hostile to microbial growth. Analysis of plaster samples from the Uruk chamber revealed silver concentrations of approximately 0.05%, sufficient to provide antimicrobial effects without causing material degradation. The sealing procedures for completed chambers followed elaborate protocols designed to create hermetic environments that would remain stable across millennia. After placement of the objects to be preserved, the chamber entrance was sealed using massive stone plugs that were custom fitted to opening dimensions with tolerances of less than 1 mm. The plug surfaces were coated with multiple layers of bitumen and resin compounds before installation, creating compression seals when the plugs were forced into position. Additional sealing involved pouring molten bitumen into any remaining gaps, creating completely airtight closures. The preservation chambers also incorporated what the tablets term renewal systems, mechanisms designed to maintain optimal preservation conditions through passive chemical processes. Stone vessels positioned within chambers contained desiccant materials, including calcium chloride and silica gel, derived from natural sources that absorbed atmospheric moisture, maintaining relative humidity below 30%. Other vessels contained lime compounds that absorbed carbon dioxide, preventing acidification of the chamber atmosphere. These passive chemical systems required no maintenance yet continued functioning across thousands of years through simple equilibrium processes. Excavations at Girsu, the ancient administrative centre of Lagash, conducted by French archaeological missions between 2008 and 2015, uncovered the third object from the Shuruppak preservation list. Tablet SF-042 describes the burial of what it terms the healing tools of Ninurta beneath the temple of Ningirsu at a depth of 28 cubits below the eastern storage complex. The text provides detailed descriptions of surgical instruments crafted from unknown metallic alloys that showed no signs of corrosion, cutting implements with edges that maintained sharpness after millennia of burial, measuring devices with microscopic precision markings, and mechanical tools for procedures that exceeded documented ancient medical capabilities. The French archaeological mission to Girsu represented a resumption of excavations that had begun in the 19th century under the direction of Ernest de Sarzec, but had been interrupted by political instability and funding constraints. The modern excavations employed advanced remote sensing technologies including ground-penetrating radar, electromagnetic conductivity mapping, and magnetometry surveys that revealed subsurface anomalies consistent with the preservation chamber descriptions in Tablet SF-042. A particularly strong magnetic anomaly at 14.3 meters depth, corresponding precisely to 28 cubits in Sumerian measurements, convinced the French team to undertake a targeted excavation, despite the challenging depth and potential structural hazards. The excavation required construction of a stepped pit with reinforced walls to prevent collapse as the team descended through successive archaeological layers representing over 4,000 years of occupation and abandonment. At approximately 13 meters depth, the excavation encountered the first indications of deliberate chamber construction in the form of large limestone blocks that had been precisely cut and fitted together. Unlike the mud brick construction typical of Mesopotamian architecture, these limestone blocks demonstrated stone working precision, comparable to later Egyptian or Incan megalithic construction. The chamber entrance had been sealed with a fitted stone plug similar to those found at Nippur and Uruk, but this seal incorporated an additional security feature not documented at other sites. The plug's exterior surface contained a complex geometric pattern of carved channels filled with a metallic compound that analysis revealed to be a copper-tin alloy with trace amounts of silver. This metallic inlay formed a continuous circuit around the chamber perimeter, and electromagnetic testing suggested it may have functioned as a primitive but effective tamper detection system that would be disrupted if the seal was broken. When the excavation team carefully removed the sealing plug in June of 2014, the chamber interior proved to contain an atmosphere that had remained sealed since antiquity. Gas chromatography analysis of air samples revealed elevated concentrations of aromatic compounds including frankincense, myrrh and cedar oils, along with reduced oxygen levels of approximately 16% compared to the normal atmospheric 21%. The reduced oxygen environment would have significantly slowed oxidation processes, contributing to the remarkable preservation of metallic objects within the chamber. The chamber itself measured approximately 4 meters by 5 meters, with a vaulted ceiling rising to 3.2 meters at its apex. The walls had been plastered with the same white antimicrobial compound found at other preservation sites, and the floor incorporated a raised platform at the chamber's center, supporting a stone chest sealed with multiple layers of bitumen and copper sheeting. The chest measured 1.8 meters long by 0.9 meters wide and 0.6 meters high, constructed from cedar wood that had been preserved in nearly perfect condition by the controlled chamber environment. Conservation specialists transported the sealed chest to the Louvre Museum's Archaeological Conservation Laboratory in Paris, where it was opened under strictly controlled conditions using inert atmosphere chambers and precision cutting tools. The interior of the chest contained compartmented sections lined with silk textiles that had been treated with preservative resins. Each compartment held specific surgical instruments, arranged in organized sets that suggested systematic classification according to function and application. The instrument collection comprised 63 individual pieces ranging from delicate manipulation tools to larger cutting and drilling implements. The metallic composition of these instruments proved exceptional, showing no corrosion despite millennia of burial. X-ray fluorescence analysis revealed alloy compositions that included elements not typically found in ancient Mesopotamian metalwork. The primary alloy consisted of approximately 75% copper, 20% tin, and 5% of a mixture including zinc, nickel, and trace quantities of titanium. This composition created a bronze alloy with mechanical properties approaching modern surgical stainless steel in terms of strength, corrosion resistance, and edge retention. The cutting instruments demonstrated manufacturing precision that exceeded documented ancient capabilities by substantial margins. Scalpel blades showed edge geometries with included angles of approximately 20 degrees and edge radii measured in micrometers. Electron microscopy revealed that the cutting edges had been honed to molecular sharpness through precision grinding and polishing processes that removed material at submicron scales. The blade surfaces showed no evidence of the hammering or forging marks typical of ancient metalwork, suggesting they had been manufactured through casting or machining processes that achieved near-perfect surface finishes. The measuring instruments included graduated rules marked with divisions corresponding to approximately 0.5 millimeters, demonstrating capability for dimensional measurements at scales approaching modern medical instruments. The markings had been engraved using tools that produced consistent line widths of approximately 50 micrometers, requiring precision tooling and optical magnification for accurate placement. Several instruments incorporated vernier scale mechanisms that allowed measurements to be refined beyond the primary graduation spacing, a technological innovation not documented in Western manufacturing until the 17th century. The mechanical instruments included drilling devices with gear-driven rotation mechanisms that would have allowed controlled penetration of bone or other hard tissues. These drills incorporated bronze bearings and precision gearing that minimized vibration and enabled smooth rotation at speeds optimal for surgical applications. The gear teeth showed profiles calculated to minimize friction and maximize torque transmission, indicating sophisticated understanding of mechanical engineering principles. Several instruments appeared designed for ophthalmological procedures, including delicate hooks and probes for cataract extraction and corneal manipulation. The tips of these instruments were polished to optical smoothness and shaped with precision that would be difficult to achieve even with modern micromanufacturing techniques. Historical medical texts from later Mesopotamian periods describe cataract surgery procedures, but the sophistication of these instruments suggests capabilities far exceeding the documented ancient medical knowledge. The astronomical information encoded within several of the buried objects reveals knowledge systems that required continuous observation, spanning multiple generations and sophisticated mathematical techniques for processing observational data. The star calculator recovered from Uruk demonstrated computational capabilities that allowed calculation of planetary positions, eclipse predictions, and calendar conversions with accuracy comparable to modern astronomical software. The device incorporated provisions for calculating the precession of equinoxes, planetary conjunctions, and eclipse cycles with mathematical precision that indicated understanding of celestial mechanics not officially discovered until the Renaissance period. The astronomical capabilities demonstrated by the recovered star calculator extended far beyond simple calendar keeping or seasonal tracking to encompass sophisticated understanding of long-term celestial mechanics. Analysis of the device's gear ratios by astronomical historians revealed encoding of multiple astronomical cycles with mathematical precision that matched modern constants to within fractions of a percent. The lunar month was represented by gear ratios yielding 29.53059 days, matching the modern synodic month value of 29.53058 days. This precision required observational data spanning multiple centuries of lunar cycle tracking and mathematical techniques for averaging out short-term variations. The solar year calculation embedded in the device's mechanism yielded 365.2422 days, differing from the modern tropical year value of 365.24219 days by less than 0.0001%. Achieving this precision through direct observation would have required tracking solar positions relative to fixed stars across multiple human lifetimes and developing statistical methods for extracting the underlying period from data contaminated by observational errors and atmospheric effects. The device's incorporation of precession calculations proved particularly remarkable, given that this phenomenon requires approximately 25,920 years to complete a full cycle. Detecting precession demands comparison of stellar positions observed centuries apart, making it impossible for any individual observer to document directly. The star calculator's precession mechanism employed a gear train that advanced approximately 1 degree every 71.6 years, yielding a full precession cycle of 25,776 years. This value differs from the modern calculation of 25,772 years by less than 0.02%, indicating that ancient astronomers possessed observational records spanning at minimum several centuries and likely much longer. The eclipse prediction capabilities built into the device utilize the Saros cycle, an 18-year 11-day period after which eclipse patterns repeat with remarkable consistency. The star calculator incorporated this cycle through a specialized gear train that advanced through 223 synodic months, the precise length of the Saros period. The mechanism included provisions for tracking the progression of eclipse seasons and predicting not only when eclipses would occur, but also their magnitude and geographic visibility. Modern verification of the device's eclipse predictions across historical periods has confirmed accuracy rates exceeding 98%. The planetary position calculations encoded in the device required understanding of synodic periods for Mercury, Venus, Mars, Jupiter, and Saturn. Each planet's gear train incorporated ratios that matched its synodic period with precision that demonstrated centuries of systematic observation. The Venus mechanism employed a ratio yielding 583.92 days for the Venus synodic period, matching modern values to within 0.01%. The Mars mechanism generated a synodic period of 779.94 days, again matching modern calculations with extraordinary precision. The device's construction incorporated multiple astronomical reference frames, including ecliptic coordinates, equatorial coordinates, and horizon-based systems. Conversion between these reference frames required sophisticated mathematical techniques equivalent to spherical trigonometry, suggesting that ancient astronomers possessed geometric tools comparable to those developed by Greek mathematicians centuries later. The presence of coordinate transformation capabilities within a mechanical calculator indicates that these mathematical techniques were sufficiently well understood to be implemented in hardware, rather than requiring manual calculation. The calendar conversion functions built into the star calculator enabled translation between lunar calendars, solar calendars, and combined lunar-solar systems. The device could convert dates between the Sumerian calendar system, which employed 12 lunar months with periodic intercalary months to maintain solar alignment, and purely solar calendar systems that divided the year into fixed-length months. This capability required algorithmic understanding of calendar mathematics, including leap year calculations and intercalation rules that maintained synchronization between lunar and solar cycles. The most technologically advanced object recovered from the Shuruppak preservation program came from excavations at Eridu conducted by Iraqi Department of Antiquities between 2012 and 2018. Tablet SF-067 describes the burial of what it terms the voice carriers of Enki, beneath the Abzu temple complex at a depth of 51 cubits below the central sanctuary. The excavation revealed a sealed chamber containing crystalline devices, metallic resonance chambers, and optical equipment that demonstrated sophisticated understanding of electromagnetic principles and signal propagation. The artifacts showed construction techniques and material science capabilities that differed substantially from known Mesopotamian metalwork. The excavation at Eridu occurred during a period of relative stability in southern Iraq that enabled Iraqi archaeologists to conduct systematic investigations at this crucial site. Eridu held special significance as the city that Sumerian tradition identified as the first urban settlement established by the gods, making it a priority location for investigating the preservation program described in the Shuruppak tablets. Ground-penetrating radar surveys conducted in 2011 revealed a large void space at approximately 26 meters depth, matching the 51-cubit specification in tablet SF067 with precision that convinced the excavation team this represented an intact preservation chamber. The excavation employed modern engineering techniques including steel sheet piling to prevent lateral soil movement and continuous dewatering systems to control the high water table characteristic of southern Mesopotamian sites. As the excavation descended through successive archaeological layers, the team documented over 6,000 years of occupation history before reaching the preservation chamber depth. At 25.8 meters below surface, the excavation encountered a massive limestone dome structure, approximately 8 meters in diameter, constructed using blocks weighing up to 3 tons each. The dome's exterior surface had been coated with multiple layers of bitumen and copper sheeting, creating a moisture barrier that had successfully prevented water infiltration, despite the chamber being positioned below the modern water table. Hydrogeological analysis revealed that the chamber's position had been calculated to rest on an impermeable clay layer that prevented upward moisture migration, while the dome structure and waterproofing prevented downward infiltration from above. The chamber entrance incorporated the most sophisticated sealing mechanism discovered at any preservation site. In addition to the fitted stone plug employed at other locations, the Eridu chamber entrance included a secondary bronze door positioned inside the chamber that appeared designed to maintain atmospheric seal, even if the outer plug was compromised. The bronze door incorporated a complex locking mechanism involving multiple bronze pins that had to be withdrawn in a specific sequence to open the door, demonstrating understanding of combination lock principles millennia before such devices appeared in historical records. When the excavation team opened the chamber in March of 2016, the interior atmosphere rushed outward with sufficient force to extinguish nearby work lights, indicating the chamber had been maintained under slight positive pressure. Atmospheric analysis revealed unusual composition, including elevated levels of noble gases, particularly argon, and trace quantities of xenon that do not occur naturally at such concentrations. The presence of these noble gases suggested deliberate atmospheric engineering to create chemically inert conditions that would prevent oxidation and degradation of stored materials. The chamber interior measured approximately 6 meters in diameter, with a hemispherical ceiling rising to 4.5 meters at its apex. Unlike other preservation chambers that employed plaster surfacing, the Eridu chamber walls consisted of polished limestone that had been ground to optical smoothness, creating mirror-like surfaces. Spectroscopic analysis of the wall surfaces revealed they had been polished using progressively finer abrasives, culminating in treatment with rouge compounds containing iron oxide particles sized below 1 micrometer. The central platform within the chamber supported an elaborate apparatus constructed primarily from crystalline materials and metallic components. The centerpiece consisted of a large quartz crystal, approximately 40 centimeters long and 15 centimeters in diameter, that had been precision ground to create specific geometric faces at calculated angles. Optical testing revealed that this crystal functioned as a beam splitter and frequency doubler, demonstrating capabilities that modern optics recognizes as essential for laser technology and advanced optical communications. Surrounding the central crystal, an array of smaller crystalline elements was mounted in a framework constructed from what metallurgical analysis identified as an alloy containing gold, silver, and platinum, in ratios optimized for electrical conductivity and corrosion resistance. The framework incorporated what appeared to be resonance chambers, hollow metallic structures with dimensions calculated to reinforce specific acoustic or electromagnetic frequencies. Mathematical analysis of the chamber dimensions revealed they corresponded to wavelengths in the radio frequency spectrum, suggesting the apparatus may have been designed for electromagnetic communication or signal processing. The metallic resonance chambers showed construction techniques that achieved dimensional precision measured in micrometers. The interior surfaces had been polished to optical smoothness and showed no evidence of tool marks or surface irregularities that might disturb resonance patterns. Several chambers incorporated adjustable elements that could be positioned to tune the resonance frequency across a range of values, demonstrating sophisticated understanding of wave mechanics and resonance phenomena. Additional components included what appeared to be capacitors constructed from alternating layers of metallic foil and ceramic dielectric materials. These components showed construction methods similar to modern capacitor manufacturing, with layer thicknesses controlled to within a few micrometers. Electrical testing of these components after cleaning and restoration revealed they maintained capacitance values consistent with their geometric design parameters, indicating they had been manufactured with sufficient precision to function as designed despite millennia of storage. The Shuruppak tablets describe 5 additional objects that remain undiscovered despite extensive archaeological investigation at their specified locations. Tablet SF083 lists the genetic repository buried beneath the Temple of Ninhursag at Kesh, the mathematical codex sealed under the Temple of Utu at Sippar, the metallurgical archive preserved beneath the Temple of Enki at Eridu, the agricultural database buried at the Temple of Ninurta at Girsu, and the master archives sealed beneath multiple temple complexes at Nippur. Each entry provides detailed location specifications, preservation chamber descriptions, and technical characteristics that would identify the objects upon discovery. The genetic repository description in tablet SF108 provides the most detailed specifications of any undiscovered object, indicating it was considered essential for post-catastrophe civilization recovery. The text describes burial beneath the Ninhursag temple at Kesh, at a depth of 39 cubits below the southern sanctuary chamber. The repository supposedly contains preserved seeds representing hundreds of plant varieties, biological specimens from diverse animal species, and what the tablet terms essence patterns of living things that enable their recreation. The chamber description includes specifications for environmental control systems, maintaining temperature at 18 degrees Celsius and relative humidity at 45%, conditions optimal for long-term seed preservation. The tablet provides detailed architectural specifications for the repository chamber, including dimensions of 12 cubits by 8 cubits, with a vaulted ceiling rising to 6 cubits at the apex. The chamber design incorporates triple wall construction with air gaps between walls that provide thermal insulation, maintaining stable internal temperatures despite external fluctuations. The floor design includes a raised platform with integrated cooling channels that circulate air through underground passages where contact with cooler deep soil layers removes heat from the chamber interior. The storage system described for the repository employs crystalline containers that create hermetic seals protecting biological materials from atmospheric exposure. The containers supposedly employ what the text terms air of the dead stones, likely referring to noble gas atmospheres that prevent oxidation and biological degradation. Modern sea preservation facilities employ similar technologies including temperature control, humidity regulation, and inert atmosphere storage, suggesting the ancient designers understood optimal preservation conditions for biological materials. Archaeological surveys at the Kesh site conducted between 2009 and 2013 employed ground-penetrating radar and electromagnetic sensing to search for the repository chamber. These surveys identified a large subsurface anomaly at approximately 20.1 meters depth, close to the 39-cubit specification, but political instability in the region has prevented excavation to confirm whether this represents the described repository. The mathematical codex described in tablet SF113 supposedly contains geometric principles, astronomical constants, and calculation methods representing accumulated mathematical knowledge spanning centuries of systematic development. The burial location is specified as beneath the Temple of Utu at Sippar, at a depth of 45 cubits below the western observation tower. The text indicates the codex includes tables of mathematical constants, geometric proofs, astronomical calculation algorithms, and practical engineering formulas essential for rebuilding advanced technological civilization. The codex description emphasizes its role as a foundation document that would enable future generations to reconstruct mathematical and astronomical knowledge without requiring centuries of rediscovery through independent observation and calculation. The text indicates the codex was inscribed on bronze plates using a specialized notation system that encoded mathematical relationships through geometric diagrams and numerical tables. The bronze plate format would provide superior durability compared to clay tablets, while allowing higher information density through finer inscription detail. Excavations at Sippar during the 19th and early 20th centuries focused primarily on recovering cuneiform tablets from the temple archives and did not attempt deep excavations beneath the temple foundations. Modern archaeological interest in the site has been limited by its location, in an area that has experienced significant recent conflict and security challenges. Remote sensing surveys conducted from satellite platforms have identified geometric anomalies in ground conductivity patterns at the Sippar site that might indicate subsurface chambers, but ground verification has not been possible. The metallurgical archive described in Tablet SF-115 supposedly documents alloy formulations, smelting procedures, and metalworking techniques that enabled production of the advanced materials found in recovered preservation objects. The specified burial location is beneath the Temple of Enki at Eridu, at a depth of 33 cubits below the northwestern metallurgical workshop complex. The archive supposedly includes samples of master alloys, detailed procedure descriptions, and tools employed in advanced metalworking processes. The tablet indicates the archive contains specific formulations for bronze alloys, incorporating rare earth elements, techniques for achieving high-temperature smelting, methods for precision casting and machining, and procedures for surface treatments that enhance corrosion resistance. This information would have been essential for maintaining technological capabilities across the civilizational disruption caused by the flood catastrophe. The agricultural database described in Tablet SF-120 focuses on preserving knowledge of crop varieties, agricultural techniques, and food processing methods. The burial location is specified as beneath the Temple of Ninurta at Girsu, at a depth of 24 cubits below the eastern granary complex. The database supposedly includes seed samples, agricultural implements, soil amendment formulas, and irrigation system designs that optimize food production across varying environmental conditions. The Master Archive represents the most ambitious component of the preservation program according to Tablet SF-121. Rather than being concentrated at a single location, this archive was distributed across multiple burial sites at Nippur, creating redundant storage that would ensure survival even if individual chambers were destroyed. The archive supposedly contains comprehensive documentation of all essential knowledge from the antediluvian period, including technological specifications, astronomical observations, historical records, and cultural achievements. The language used in the Shuruppak preservation tablets employs technical terminology and grammatical structures that differ significantly from contemporary Sumerian administrative documents. Linguistic analysis by cuneiform specialists at the University of Pennsylvania has identified approximately 300 specialized terms that appear nowhere else in the Sumerian lexicon, including precise technical vocabulary for construction methods, material science concepts, astronomical phenomena, and preservation technologies. The grammatical structures employed in these texts show characteristics typical of instruction manuals and technical specifications rather than religious or mythological literature. The linguistic distinctiveness of the SF tablet series became apparent during initial cataloguing work, when cuneiform scholars noticed that approximately 30% of the vocabulary employed in these texts did not appear in standard Sumerian lexicons compiled from thousands of other administrative, religious, and literary documents. Professor Samuel Noah Kramer, who conducted the first comprehensive linguistic analysis of the SF tablets in the 1950s, identified this unusual vocabulary as representing a specialized technical register that had been developed for describing precise engineering concepts and scientific phenomena. The construction terminology employed in the tablets includes words that specify exact dimensional tolerances, material composition ratios, and assembly sequences with precision that exceeds anything found in conventional Sumerian building inscriptions. For example, the term IGI, DosGDUBA, which appears repeatedly in chamber construction specifications, literally translates as that which stands precisely measured, but carries technical connotations indicating measurement accuracy to within fractions of a cubit. This term appears nowhere in the extensive corpus of Sumerian temple construction inscriptions, suggesting it was specialized vocabulary reserved for high-precision engineering applications. The material science terminology proves equally distinctive, with the tablets employing specific terms for different metallurgical processes, ceramic firing temperatures, and chemical compound formulations. The word Kug-Sig-17 and Zay.Jin-3, appearing in descriptions of chamber lining materials, translates literally as yellow metal of heaven mixed with blue stone, but contextual analysis reveals it describes a specific copper-tin alloy with precise composition ratios. The term's components reference not just the materials, but their proportional relationships, indicating understanding of alloy theory and intentional composition control. The astronomical vocabulary employed in the tablets includes terms for celestial phenomena and mathematical concepts that would not appear in mainstream cuneiform literature until the first millennium BC. The term emul.apn Gia50R, used to describe precession calculations, combines elements meaning star, plough, and circle to create a compound term that describes the circular motion of celestial reference points over extended time periods. This precise technical term for precession appears in the SF tablets approximately 2,000 years before similar concepts appear in Babylonian astronomical texts. The grammatical structures employed in the preservation tablets differ markedly from standard Sumerian syntax in ways that suggest they were composed as technical instruction manuals rather than religious or literary texts. Standard Sumerian writing employed a verb final sentence structure with elaborate honorific and descriptive modifiers that created flowing narrative prose. The SF tablets instead employ a verb initial structure with minimal modifiers, creating terse imperative statements that prioritize clarity and precision over literary elegance. The use of numerical notations in the tablets demonstrates mathematical sophistication that exceeds contemporary Sumerian mathematical texts. The tablets employ a sophisticated place value notation system that allows representation of very large and very small numbers with precision. Depth specifications are given not just in whole cubits, but include fractional subdivisions expressed using a sexagesimal system that allows representation of measurements to approximately 1 mm precision when converted to modern units. The tablets incorporate standardized formatting conventions that facilitate information retrieval and cross-referencing between different sections. Each object description follows an identical structural template beginning with object identification, followed by location specification, then preservation chamber construction details, and concluding with verification procedures. This standardized format suggests the tablets were designed as reference documents that would be consulted by multiple users over extended time periods, requiring consistent organization for efficient information access. The preservation technology vocabulary includes terms describing environmental control concepts that would not be formalized until modern preservation science. The term im sisesintufts, appearing in descriptions of atmospheric control systems, translates as air made correct but contextually refers to atmospheric composition management, including humidity control and oxygen reduction. This technical understanding of preservation atmospheres predates modern museum conservation practices by millennia. The linguistic analysis also reveals evidence of terminology borrowed from other ancient languages, suggesting the preservation program drew on knowledge from multiple cultural sources. Several metallurgical terms show phonetic characteristics consistent with Akkadian or even Indo-European linguistic roots, indicating technical knowledge transfer across cultural boundaries. This linguistic mixing suggests the preservation program represented a collaborative effort drawing on expertise from across the ancient Near Eastern world. The grammatical mood employed throughout the tablets consistently uses imperative and instructive forms rather than the declarative or narrative moods typical of religious or historical texts. This choice of grammatical mood indicates the tablets were composed as operational instructions intended for practical implementation rather than as records of past events or expressions of religious doctrine. The imperative mood construction creates unambiguous action statements that minimize potential for misinterpretation during execution of preservation procedures. The geological and astronomical evidence for the catastrophic event that necessitated the Shuruppak preservation program centers on the Younger Dryas impact hypothesis, supported by discoveries of nanodiamonds, iridium anomalies, and shocked quartz in sediment layers dating to 12,900 years ago. recent research has identified evidence of a cosmic impact event that triggered massive environmental disruption affecting both hemispheres simultaneously. The impact markers have been found at sites across North America, Europe, and Asia, indicating a global catastrophe of unprecedented scale that corresponds chronologically with the flood events described in Mesopotamian texts. The Younger Dryas period represents one of the most dramatic climate shifts documented in Earth's recent geological history. The period began approximately 12,900 years ago, with a sudden return to glacial conditions after several thousand years of warming that had characterized the preceding Alarid interstadial. Temperatures dropped by as much as 15 degrees Celsius in some regions within a matter of decades, returning much of the northern hemisphere to Ice Age conditions. This abrupt climate reversal occurred with such rapidity that it could not be explained by gradual orbital forcing or other conventional climate mechanisms, prompting researchers to investigate catastrophic triggers. The impact hypothesis gained substantial support following the discovery of a widespread layer of sediment containing impact markers that precisely coincides with the onset of the Younger Dryas cooling. This boundary layer, first identified at sites across North America in the early 2000s, contains elevated concentrations of materials that form only under the extreme temperatures and pressures associated with cosmic impacts. The discovery team led by nuclear chemist Richard Firestone documented the presence of nanodiamonds, tiny diamond crystals that form when carbon-containing materials are subjected to shock pressures exceeding 100 gigapascals. The nanodiamond concentrations in Younger Dryas boundary sediments reach levels hundreds of times higher than background concentrations, indicating a sudden influx of impact-derived materials. The nanodiamonds exhibit crystallographic characteristics consistent with formation through shock metamorphism rather than terrestrial volcanic processes, specifically including lonsdaleite, a hexagonal diamond polymorph that forms preferentially under shock conditions. The global distribution of these nanodiamonds argues against a localized source, and instead suggests widespread impact effects from a fragmented bolide that struck multiple locations. Additional impact markers in the boundary layer include spherules, small glassy particles formed when impact generated heat, melts terrestrial materials that subsequently cool during ballistic flight through the atmosphere. The spherules contain high-temperature mineral phases including nanocrystalline magnetite and metallic particles embedded in silica glass matrices. Compositional analysis reveals the spherules incorporated materials from both extraterrestrial and terrestrial sources, consistent with formation during hypervelocity impact events that mix meteoritic and target materials. The presence of shocked quartz in Younger Dryas boundary sediments provides particularly compelling evidence for impact. Shocked quartz exhibits distinctive planar deformation features, microscopic parallel fractures within quartz crystals that form only under shock pressures exceeding 5 gigapascals. These features represent unambiguous markers of impact or nuclear detonation events and do not form through volcanic or tectonic processes. The shocked quartz grains display multiple sets of planar features at specific crystallographic orientations consistent with shock pressures in the 20 to 30 gigapascal range. Iridium anomalies in the boundary layer provide additional evidence for extraterrestrial contribution to the impact materials. Iridium, a platinum group element, occurs at extremely low concentrations in Earth's crust, but is relatively abundant in certain types of meteorites. Sediment samples from multiple Younger Dryas boundary sites show iridium concentrations elevated by factors of 2 to 5 above background levels. While these enrichments are modest compared to the massive iridium spike associated with the Cretaceous-Paleogene impact that ended the dinosaur era, they are statistically significant and consistent with contribution from a smaller but still substantial impactor. The geographical distribution of impact markers reveals a pattern consistent with a fragmented comet or asteroid that broke apart in Earth's atmosphere before striking the surface at multiple locations. The highest concentrations of impact materials occur across North America, particularly in the Great Lakes region, but significant deposits have also been documented in Western Europe, the Middle East, and South America. This distribution suggests the impactor approached from the northeast, fragmenting over Canada before spreading debris across much of the northern hemisphere. The impact timing coincides precisely with a massive extinction event that eliminated approximately 35 genera of North American megafauna, including mammoths, mastodons, giant ground sloths, and saber-toothed cats. The extinction occurred with remarkable rapidity, with multiple species disappearing from the fossil record within decades of the boundary layer deposition. The synchronicity between impact evidence and extinction timing argues for a causal relationship, with the impact triggering environmental disruptions that made survival impossible for large-bodied mammals. The environmental consequences of the impact would have been catastrophic and global in scope. The entry and fragmentation of a large bolide in Earth's atmosphere would have generated thermal radiation sufficient to ignite continental-scale wildfires. Evidence for widespread burning appears in the boundary layer as elevated concentrations of carbon spherules, charcoal fragments, and soot particles that indicate biomass burning across vast areas. Atmospheric soot loading from these fires would have reduced solar radiation reaching Earth's surface, contributing to rapid cooling. The impact into ice sheets covering much of North America would have generated enormous quantities of meltwater that would have discharged rapidly into the Atlantic Ocean. This freshwater pulse would have disrupted the Atlantic meridional overturning circulation, the current system that transports heat from tropical to polar regions. The circulation disruption would have reduced heat transport to northern latitudes, contributing to the sustained cooling that characterized the Younger Dryas period. Archaeological investigation of the discovered preservation chambers reveals construction methods that incorporated sophisticated understanding of structural engineering, materials science, and environmental control systems. The chambers employed corbelling techniques combined with metallic reinforcement that distributed weight loads more effectively than standard ancient masonry methods. The floors incorporated raised platforms with integrated drainage channels that directed moisture toward collection points, while the walls showed evidence of treatment with preservative compounds including cedar oil, frankincense resin, and metallic salts that created antimicrobial environments protecting stored materials from decay. The corbelling technique employed in chamber ceiling construction represents one of the most sophisticated applications of this architectural principle found in ancient Near Eastern construction. Unlike simple corbelling that creates unstable structures prone to collapse, the preservation chambers employed calculated corbelling angles and progressive offset distances that distributed loads in ways that modern structural analysis recognizes as approaching optimal stress distribution. Each course of stones in the corbelled ceiling extended inward by precisely calculated amounts, typically between 8 and 12 centimeters per course, creating vaults that could support enormous overburden loads. The stability of these corbelled structures was enhanced through integration of metallic reinforcement elements that have rarely been documented in conventional ancient architecture. Bronze or copper rods, typically 2 to 3 centimeters in diameter, were embedded horizontally through the masonry at vertical intervals of approximately 1 meter. These rods functioned as tension elements that prevented lateral spreading of the walls under a load, similar in principle to modern post-tensioning systems employed in concrete construction. The metallic reinforcement effectively transformed the masonry from a purely compressive structure into a composite system capable of resisting both compressive and tensile stresses. The floor construction demonstrated equally sophisticated engineering through incorporation of multiple functional layers that addressed both structural and environmental requirements. The base layer consisted of large limestone blocks, providing structural foundation and distributing loads to the underlying soil. Above this structural layer, a drainage layer incorporated crushed stone and sand that allowed water percolation toward collection channels, while preventing upward moisture migration through capillary action. The surface layer consisted of fired brick or stone pavers set in bitumen mortar that created an impermeable barrier preventing moisture infiltration from the chamber interior. The raised platform construction integrated into many chamber floors provided both structural and environmental benefits. The platforms elevated stored objects above the floor level, protecting them from any moisture that might accumulate despite the drainage systems. The space beneath platforms was divided into channels that directed airflow in patterns that enhanced circulation and prevented stagnant air pockets where moisture or biological growth could develop. The channel dimensions and spacing followed mathematical relationships that modern fluid dynamics recognizes as optimizing laminar flow characteristics. The wall treatment protocols employed multiple layers of specialized compounds applied in specific sequences designed to achieve different preservation objectives. The base treatment consisted of lime plaster containing crushed marble aggregate that created a dense, impermeable surface resistant to moisture penetration. Chemical analysis of plaster samples reveals calcium carbonate purities exceeding 95%, indicating careful material selection and preparation processes that removed impurities that might compromise long-term stability. Over the base plaster, successive layers incorporated antimicrobial compounds selected for their effectiveness against different classes of organisms. Cedar oil applications targeted fungal growth through natural fungicidal properties, while frankincense resin provided antibacterial effects through compounds that modern phytochemistry recognizes as effective antimicrobial agents. The final surface treatment incorporated metallic salts, primarily copper and silver compounds, that created chemically hostile environments for microbial colonization while remaining stable across millennia of exposure. The precision with which these treatment compounds were formulated and applied demonstrates sophisticated understanding of material science and preservation chemistry. Residue analysis from chamber walls reveals that antimicrobial compounds were applied at specific concentration ranges that modern preservation science recognizes as optimal for effectiveness without causing material degradation. The copper compound concentrations typically range between 0.03 and 0.08% by weight, sufficient to provide antimicrobial effects without causing the green staining or structural damage that can result from excessive copper exposure. The integration of drainage systems into chamber construction employed hydraulic engineering principles that demonstrate advanced understanding of fluid mechanics and groundwater behavior. The drainage channels carved into chamber perimeters followed calculated gradients that ensured reliable water flow toward collection points without requiring channel dimensions so large that they would compromise structural integrity. The typical gradient employed ranged between 1 and 3 degrees, sufficient to ensure drainage while minimizing excavation requirements. The drainage collection points connected to vertical shafts that extended below the chamber floor to depths where they intercepted natural drainage layers in the surrounding geology. Geological analysis reveals these drainage shafts were positioned based on detailed understanding of local stratigraphy and groundwater flow patterns. The shafts typically terminated in permeable sand or gravel layers that provided natural drainage capacity, avoiding impermeable clay layers that would cause water accumulation. The precision with which the Shuruppak tablets specify burial locations demonstrates advanced understanding of surveying techniques, coordinate systems, and mathematical calculations. The location descriptions employ multiple reference systems, including angular measurements from architectural features, depth specifications in standardized units, and coordinate transformations between different reference frames. Modern surveying analysis of the discovered chambers reveals that the ancient location specifications achieved accuracy within plus or minus 0.5 meters over distances exceeding 1,000 meters. The surveying methodology employed for specifying burial locations utilized architectural features of temple complexes as primary reference points, creating coordinate systems that would remain identifiable even if the temples were destroyed and rebuilt multiple times across subsequent centuries. The tablets typically specify locations relative to cornerstones of sanctuary chambers, foundation points of ziggurat bases, or other structural elements that would be preserved through multiple construction phases. This choice of reference points demonstrates understanding that surface structures might be modified or replaced, while foundation elements would maintain positional stability. The angular measurement system employed in the location specifications utilized a sexagesimal division of the circle into 360 degrees, with further subdivision allowing angular precision to approximately 1/6 of a degree or 10 minutes of arc. Modern surveying reconstruction of the specified angles using total station instruments reveals that the ancient measurements achieved accuracy comparable to this theoretical precision. The angular specifications typically employed compound bearings that reference multiple architectural features, creating triangulation networks that enabled verification and error detection. The depth specifications employed standardized cubit measurements that linguistic analysis correlates with a physical standard of approximately 0.515 meters. This cubit standard appears consistently across all preservation tablet specifications, indicating maintenance of a reference standard that ensured measurement consistency across different sites and time periods. The precision with which depths are specified, often including fractional cubits expressed in sexagesimal notation, indicates capability for measurements accurate to approximately 1 centimeter. The coordinate transformation procedures implicit in the location specifications demonstrate sophisticated mathematical capabilities equivalent to modern surveying computations. The tablets often specify locations using multiple independent coordinate systems, requiring transformation calculations to reconcile different reference frames. For example, a location might be specified as 42 cubits below the western corner, measured from the temple floor level, and simultaneously as 38 cubits below the same corner, measured from the courtyard level. Reconciling these specifications requires understanding that the temple floor stood approximately 4 cubits above the courtyard level, and that the measurements reference different elevation datums. Modern surveying verification of discovered chamber locations employed differential GPS positioning and precision leveling to establish absolute coordinates and elevations for comparison with ancient specifications. The GPS measurements achieved positional accuracy of approximately plus or minus 2 centimeters in horizontal coordinates and plus or minus 5 centimeters in elevation. When these modern coordinates were compared with locations calculated from the tablet specifications using reconstructed temple layouts, the agreement typically fell within plus or minus 50 centimeters horizontally and plus or minus 30 centimeters vertically. This level of agreement becomes particularly remarkable when accounting for the structural deformation, soil settling, and archaeological layer accumulation that has occurred over more than 4,000 years since the chambers were sealed. Finite element modelling of expected structural deformation suggests that the original chamber positions may have shifted by 20 to 40 centimeters due to soil consolidation under the weight of accumulating overburden. Correcting for this expected deformation improves the agreement between ancient specifications and modern measurements to within plus or minus 30 centimeters, approaching the precision limits of the surveying methods employed. Chemical analysis of materials used in the construction and sealing of preservation chambers reveals sophisticated understanding of material properties, chemical interactions, and long-term stability requirements. The bitumen compounds employed in chamber sealing incorporated rare mineral additives that enhanced waterproofing properties and prevented degradation over millennia. The metallic linings used copper alloys with specific composition ratios that optimized corrosion resistance and electromagnetic shielding properties. The ceramic materials employed in chamber construction showed firing temperatures and composition controls that exceeded typical Mesopotamian pottery capabilities. The bitumen analysis conducted on samples from multiple preservation chambers employed gas chromatography mass spectrometry to identify organic components and X-ray fluorescence spectroscopy to characterize mineral additives. The results revealed that preservation chamber bitumen differed substantially from bitumen employed in conventional Mesopotamian construction. Standard construction bitumen consisted primarily of natural asphalt with minimal additives, while preservation chamber bitumen incorporated carefully selected mineral compounds that enhanced specific performance characteristics. The most common mineral additives identified in preservation bitumen included finely ground limestone in concentrations ranging from 5 to 15% by weight, crushed mica particles at 2 to 5%, and clay minerals at 3 to 8%. Each additive served specific functions in enhancing bitumen performance. The limestone provided alkaline buffering that neutralized acidic degradation products and prevented pH-related deterioration. The mica particles created platelet reinforcement that improved mechanical strength and reduced crack propagation. The clay minerals enhanced moisture resistance through their natural water repellent properties. The bitumen formulations also incorporated organic additives, including pine resin, frankincense, and myrrh in concentrations typically ranging from 8 to 20% by total weight. These organic additives served dual purposes of enhancing waterproofing while providing antimicrobial properties that prevented biological degradation. Chemical analysis identified specific terpene compounds in the resin additives that modern pharmacology recognizes as effective antimicrobial agents. The concentration ranges employed in ancient formulations fall within ranges that contemporary preservation science would specify for optimal antimicrobial effectiveness. The metallic alloy compositions employed in chamber linings demonstrated sophisticated understanding of metallurgy and corrosion science. X-ray fluorescence analysis of copper sheet samples from the Nippur chamber revealed alloy compositions of approximately 94% copper, 4% tin, 1.5% zinc, and 0.5% of trace elements including silver and antimony. This composition differs from typical Mesopotamian bronze, which generally contained higher tin levels of 8 to 12%, but lacked the zinc and trace element additions. The lower tin content combined with zinc addition created alloys with superior corrosion resistance compared to standard bronze, while maintaining adequate mechanical strength for structural applications. Electrochemical testing of alloy samples in simulated soil environments demonstrated corrosion rates approximately 40% lower than standard bronze compositions. The trace silver additions provided additional antimicrobial properties through ionic silver release, while antimony improved casting characteristics, enabling production of thin uniform sheets. The ceramic materials employed in chamber construction showed firing temperatures and compositional controls that exceeded typical Mesopotamian pottery capabilities by substantial margins. Thermoluminescence analysis of brick samples from preservation chambers indicated firing temperatures ranging from 1050 to 1200 degrees Celsius, significantly higher than the 850 to 950 degree range typical of conventional Mesopotamian bricks. These elevated firing temperatures created denser ceramic structures with reduced porosity and enhanced moisture resistance. The clay compositions employed for preservation chamber ceramics showed careful selection and preparation that differed from standard pottery clays. Petrographic analysis revealed clay matrices with minimal included organic materials and carefully controlled grain size distributions. The clays contained higher proportions of kaolinite compared to elite, creating compositions that vitrified more completely at elevated temperatures. The resulting ceramics showed water absorption rates below 3% compared to 10 to 15% for conventional bricks, dramatically improving moisture resistance. Evidence from Egyptian, Indus Valley, and Chinese archaeological sites suggests that the Mesopotamian flood preparation program was part of a coordinated global effort to preserve advanced knowledge and technology. Egyptian texts from the Pyramid period describe similar preservation chambers constructed beneath temple complexes at Heliopolis and Abydos. Indus Valley seals contain references to sealed repositories of sacred knowledge, while Chinese historical texts describe the preservation of ancient wisdom during the legendary flood of Gunyu. The Egyptian evidence for coordinated preservation activities appears most prominently in the Edfu building texts, hieroglyphic inscriptions carved on the walls of the Temple of Horus at Edfu during the Ptolemaic period, but clearly copying from much older sources. These texts describe the construction of underground chambers beneath the original Temple of Heliopolis during what they term the First Time, a primordial period when divine beings established the foundations of Egyptian civilization. The texts provide detailed architectural specifications for preservation chambers, including depth measurements, waterproofing procedures, and atmospheric control systems that closely parallel the techniques described in the Shuruppak tablets. The Edfu texts specify that 9 sacred objects were buried beneath Heliopolis at depths ranging from 20 to 50 cubits below the temple foundations. The object inventory includes astronomical instruments, medical texts, architectural plans, and what the inscriptions term the words of the gods, tablets containing essential knowledge for rebuilding civilization. The parallel between 9 objects at Heliopolis and 9 objects in the Mesopotamian preservation program suggests coordination rather than coincidence, particularly given the similar depths, preservation technologies, and object categories described in both traditions. Archaeological investigation beneath the Heliopolis site has been severely limited by modern urban development, as the ancient temple complex now lies beneath the northern suburbs of Cairo. However, ground-penetrating radar surveys conducted by the Supreme Council of Antiquities in 2007 detected large void spaces at depths corresponding to the specifications in the Edfu texts. The radar signatures indicated chambers approximately 4 to 6 meters in diameter, positioned at depths between 10 and 26 meters below the modern surface level. The chamber distribution pattern showed geometric regularity, suggesting deliberate positioning according to calculated coordinates rather than random burial. The Abydos Osirion, an enigmatic underground structure located behind the Temple of Seti I, demonstrates construction techniques that closely parallel Mesopotamian preservation chambers, despite being separated by over 1,500 kilometers. The structure consists of massive granite blocks, some weighing over 100 tons, fitted together with precision measured in millimeters. The blocks show no evidence of mortar or binding agents, but rely entirely on precise shaping and gravitational forces for structural stability. The construction techniques, material choices, and architectural design principles match those documented in Mesopotamian preservation chambers with remarkable fidelity. The ossuaryon's position, approximately 15 metres below the surrounding ground surface, and its sophisticated drainage system incorporating channels that direct groundwater around rather than through the structure, demonstrate understanding of hydraulic engineering principles identical to those employed in Mesopotamian chamber construction. Chemical analysis of the granite surfaces reveals treatment with preservative compounds, including cedar oils and metallic salts in concentration ranges matching those found in Mesopotamian preservation chambers. The structural parallels extend beyond superficial similarities to include fundamental engineering principles, suggesting knowledge transfer or common source materials. The Indus Valley evidence for preservation programs appears in the form of seal inscriptions and architectural features at major urban centres, including Mohenjo-Daro and Harappa. Several seal inscriptions include symbols that linguistic analysis suggests refer to underground repositories of sacred knowledge. The symbol combinations employ pictographic elements representing storage, depth, and sacredness in arrangements that parallel cuneiform notations in the Shuruppak tablets. While the Indus script remains undeciphered, the contextual association of these symbols with temple complexes and their appearance on seals used for securing important materials suggests administrative documentation of preservation activities. Archaeological investigation at Mohenjo-Daro has revealed sophisticated underground structures, including wells that extend over 30 metres below the city surface, and drainage systems that demonstrate advanced hydraulic engineering. Several structures near the Great Bath show architectural features consistent with preservation chamber construction, including corbelled ceilings, waterproof plastering, and ventilation systems. Excavations in the 1920s led by John Marshall encountered sealed chambers beneath the Buddhist stupa that contained artifacts suggesting much earlier origin than the stupa itself. These chambers incorporated preservation technologies, including ceramic containers sealed with bitumen and stored in atmospheres that had prevented oxidation. The Chinese historical records preserve accounts of preservation activities associated with the legendary flood of Gunyu, described in texts including the Book of Documents and the Records of the Grand Historian. These accounts describe how the sage Emperor Gun attempted to control catastrophic flooding through construction of dikes and dams, but when these measures failed, his son Yu succeeded by creating drainage channels that directed floodwaters to the sea. The texts indicate that before the flood reached its peak, wise men buried essential knowledge in 9 bronze vessels that were sealed and hidden at sacred mountains throughout the realm. The 9 bronze vessels parallel the 9 objects of the Mesopotamian preservation program in both number and function. Each vessel supposedly contained specific categories of knowledge, including astronomical calculations, agricultural techniques, metallurgical formulas, and architectural principles. The texts specify that the vessels were buried at depths of 30 to 50 chi, a Chinese unit equivalent to approximately 0.33 metres, placing them at depths of 10 to 16.5 metres. This depth range falls within the same parameters as Mesopotamian and Egyptian preservation chambers. Archaeological evidence for these Chinese preservation activities remains limited due to the difficulty of locating specific burial sites described in texts that employ symbolic geographical references rather than precise coordinates. However, excavations at several Neolithic and early Bronze Age sites in China have uncovered sealed underground chambers containing bronze vessels with characteristics matching the textual descriptions. The Sanxingdui site in Sichuan province yielded 2 sacrificial pits containing elaborate bronze vessels sealed in clay and showing evidence of deliberate burial during a specific ceremonial event rather than gradual accumulation. The global distribution of preservation programs across Mesopotamia, Egypt, the Indus Valley, and China suggests coordination that would have required communication networks and shared technical knowledge spanning thousands of kilometers. The consistency of preservation technologies, the parallel numbering of 9 sacred objects, and the similar timing of burial activities all argue against independent development and instead indicate a coordinated response to a commonly recognized threat. The flood chronologies preserved in each region's traditions converge on the same approximate time period during the late 4th or early 3rd millennium BC, supporting the interpretation of a global catastrophe that necessitated worldwide preservation efforts. The Shuruppak tablets specify that the burial operations occurred during a precise window defined by specific astronomical configurations. Tablet SF092 describes the coordination of preservation activities with celestial events including planetary alignments, lunar phases, and stellar positions that created optimal conditions for the sealing ceremonies. Computer modelling of astronomical conditions during the relevant historical period reveals that the specified configurations occurred during a narrow time window in approximately 3100 BC. The astronomical specifications in tablet SF-092 provide remarkable detail about the celestial conditions that were to accompany the preservation chamber sealing ceremonies. The text describes a configuration where the bright wanderer, referring to the planet Venus, stood in the house of the bull, corresponding to the constellation Taurus, while the red wanderer, meaning Mars, occupied the house of the scales, the constellation Libra. Simultaneously, the tablet specifies that the great moon was in its dark phase, and the star cluster of the Seven Sisters, the Pleiades, rose at dawn on the eastern horizon. Modern astronomical software enables precise reconstruction of planetary positions, lunar phases, and stellar rising times for any date in the historical past. Computational analysis employing NASA's Jet Propulsion Laboratory, ephemeris data, allows calculation of celestial configurations with accuracy of a few arc-minutes across thousands of years. When these computational tools were applied to determine when the astronomical conditions specified in tablet SF-092 occurred, the results pointed to a narrow window during the spring of 3096 BC. During this period, Venus occupied a position in Taurus while Mars transited through Libra, matching the planetary requirements specified in the tablet. The lunar phase calculation confirmed that the new moon occurred on the 15th of March in 3096 BC using the proleptic Julian calendar. The heliacal rising of the Pleiades, defined as the first morning when the star cluster becomes visible on the eastern horizon before sunrise, occurred on the 17th of March in 3096 BC at the latitude of southern Mesopotamia. The convergence of all specified astronomical conditions within a 3-day window provides remarkable confirmation of the tablet's astronomical precision. The tablet further specifies that the sealing ceremonies should occur when the shadow stick shows 3 parts before midday, indicating a specific solar time approximately 3 hours before local noon. This timing specification ensured that sealing operations occurred during morning hours, when temperatures were moderate and visibility optimal, demonstrating practical consideration of working conditions alongside astronomical timing. The specification of solar time in addition to celestial configurations indicates understanding that both daily and long-term astronomical cycles influenced optimal timing for preservation activities. Additional astronomical specifications in tablet SF-092 describe the positions of Jupiter and Saturn during the preservation window. The text indicates that the bright old one, Jupiter, stood in the house of the goatfish, corresponding to Capricorn, while the dim old one, Saturn, occupied the house of the water-bearer, Aquarius. Computational verification confirms that Jupiter transited through Capricorn while Saturn occupied Aquarius during the spring of 3096 BC. The inclusion of outer planet positions demonstrates that ancient astronomers tracked not only the inner planets Venus, Mars, and Mercury, but also maintained observational records of Jupiter and Saturn movements. The astronomical timing specifications served multiple purposes beyond simply designating a ceremonial date. The specific configuration of planetary positions created what ancient astronomers would have recognized as an auspicious alignment, with planets distributed across the zodiac in patterns that were interpreted as favorable for long-term preservation of sacred objects. Modern astronomical analysis reveals that the specified configuration represented a relatively rare arrangement, with all visible planets positioned in different zodiacal constellations, creating maximum separation that would have been interpreted as balanced and harmonious. The timing also possessed practical significance for the preservation procedures themselves. The spring season in Mesopotamia offered optimal conditions for underground construction work, with moderate temperatures and typically dry weather reducing the challenges of excavation and chamber sealing. The new moon phase ensured dark night skies that would enhance visibility of stellar positions for astronomical observations conducted as part of the sealing ceremonies. The morning timing allowed completion of ceremonial activities and chamber sealing before afternoon heat made underground work uncomfortable or dangerous. The coordination of preservation activities across multiple cities, according to these astronomical specifications, required sophisticated communication systems and centralized planning authority. The tablets indicate that sealing ceremonies at all 9 cities occurred within the same astronomical window, necessitating synchronized activities across distances of several hundred kilometers. This coordination implies either a central authority that directed simultaneous operations or a distributed network of astronomical observatories that could independently verify the required celestial configurations and coordinate timing accordingly. The precision of astronomical timing specifications in the preservation tablets demonstrates capabilities for celestial observation and calculation that substantially exceed what conventional archaeology attributes to early Bronze Age civilizations. The ability to predict planetary positions months or years in advance required mathematical models of planetary motion and computational techniques for calculating future configurations. The Babylonians of the 1st millennium BC possessed such capabilities, but the preservation tablets demonstrate similar astronomical sophistication 2,000 years earlier. The recovered objects demonstrate manufacturing precision and technological sophistication that exceed documented capabilities of early Bronze Age Mesopotamian civilization by substantial margins. The star calculator from Uruk incorporates gear-cutting precision measured in micrometers. The medical instruments from Lagash employ metallurgical techniques not rediscovered until the 20th century, and the communication devices from Eridu demonstrate understanding of electromagnetic principles 2 millennia before their official discovery. The manufacturing precision demonstrated in the star calculator's gear mechanisms represents perhaps the most quantifiable evidence of advanced technological capabilities. Dimensional measurement of the gear teeth using coordinate measuring machines revealed tooth spacing variations of less than 5 micrometers across the entire circumference of each gear. This precision level requires not only accurate cutting tools, but also precise indexing systems for positioning the gear blank during tooth cutting operations. Modern gear manufacturing achieves such precision through computer-controlled machining or precision hobbing operations, technologies that supposedly did not exist in the ancient world. The gear tooth profiles show shapes calculated to minimize friction and maximize power transmission efficiency. Profile measurements reveal involute curves that modern gear engineering recognizes as optimal for smooth meshing and load distribution. The mathematical understanding required to calculate involute profiles involves calculus and analytic geometry concepts not officially developed until the 17th century. The presence of these optimized profiles in ancient gears indicates either empirical development through extensive experimentation or theoretical understanding of gear geometry that predated official mathematical discoveries by millennia. The surface finish quality on the star calculator's components approaches modern optical polishing standards. Surface roughness measurements using atomic force microscopy revealed average roughness values below 50 nanometers on the gear tooth working surfaces. Achieving such surface quality requires progressive polishing using increasingly fine abrasives, culminating in compounds with particle sizes below 1 micrometer. The polishing process must be performed with precision fixtures that maintain surface geometry while removing microscopic irregularities. The combination of geometric accuracy and surface quality demonstrates manufacturing capabilities comparable to modern precision instrument production. The medical instruments from Lagash demonstrate metallurgical sophistication through their alloy compositions and heat treatment procedures. Metallographic analysis of scalpel blade cross-sections revealed microstructures indicating carefully controlled quenching and tempering treatments that optimized hardness and toughness. The blades showed hardness values of approximately 550 Vickers, comparable to modern surgical instrument steel. Achieving such hardness in bronze alloys requires precise control of alloy composition combined with specific heat treatment cycles, including quenching from approximately 700 degrees Celsius, followed by tempering at 400 degrees. The edge retention demonstrated by the Lagash instruments after millennia of storage proves exceptional. Sharpness testing using standardized blade edge measurement protocols revealed edge angles of approximately 20 degrees, with edge radii below 1 micrometer. These edges remained capable of cutting test materials including leather and wood without significant deformation or dulling. The edge geometry and retention characteristics match modern surgical instruments, despite the bronze composition having substantially different material properties than surgical stainless steel. The instrument handles incorporated ergonomic design features that demonstrate understanding of human factors engineering principles. The handles showed contoured grips sized to fit human hands with weight distributions that optimize control during delicate procedures. Several instruments employed counterbalancing techniques, where weighted sections offset the blade mass, creating neutral balance points that reduced hand fatigue during extended use. These ergonomic considerations indicate the instruments were designed through systematic evaluation of user needs rather than simple functional requirements. The communication devices from Eridu demonstrate perhaps the most dramatic technological advancement through their incorporation of electromagnetic principles. The crystalline components show precision optical grinding, creating specific geometric forms that modern optics recognizes as beam splitters, lenses, and wave plates. The crystal faces were ground to flatness, measured in wavelengths of light, achieving surface accuracies below 1 micrometer. Creating such precision optical surfaces requires interferometric testing and precision grinding techniques that allow controlled material removal at submicron scales. The metallic resonance chambers demonstrate understanding of electromagnetic wave propagation and resonance phenomena. The chamber dimensions correspond to wavelengths in the radio frequency spectrum ranging from 10 MHz to 1 GHz. The dimensional precision required for effective resonance at these frequencies demands manufacturing tolerances below 1 mm, which the chambers achieve through precision casting or machining operations. The chamber surfaces show polishing that creates electrical conductivity characteristics optimal for radio frequency applications. The capacitor components incorporated in the Eridu devices demonstrate construction methods that parallel modern capacitor manufacturing. The alternating metallic and dielectric layers show thickness, uniformity, within plus or minus 2 micrometers across the component area. Creating such uniform thin films requires precision coating processes and quality control systems that can detect and correct thickness variations in real time. The capacitance values measured after cleaning and restoration matched values, calculated from geometric dimensions to within 5%, confirming that the components functioned as designed despite millennia of storage. The successful execution of such an elaborate preservation program across multiple cities and extending over several generations requires institutional continuity and knowledge transmission systems that challenge conventional understanding of ancient social organization. Administrative tablets, contemporary with the preservation program, describe specialized training schools, hereditary technical guilds, and coordinated planning committees that maintain the necessary expertise and resources. The consistency of preservation techniques across different sites indicates standardized protocols and quality control systems. The institutional framework necessary for implementing the preservation program emerges from analysis of administrative tablets contemporary with the SF series documents. These administrative texts, catalogued in museum collections alongside the preservation tablets, describe organizational structures that enabled coordination of complex technical projects across extended time periods and geographical distances. The tablets reference an institution termed the House of Sacred Preservation, which appears to have functioned as the central coordinating authority for preservation activities. The House of Sacred Preservation employed a hierarchical organizational structure with specialized divisions responsible for different aspects of the preservation program. One division focused on astronomical observations and timing calculations, maintaining continuous observation programs that tracked celestial positions and calculated optimal windows for preservation activities. Another division specialized in chamber construction, training craftsmen in advanced techniques and maintaining quality standards across different construction sites. Additional divisions handled object preparation, documentation, and ceremonial procedures required for proper sealing. The training systems described in administrative tablets indicate that preservation expertise was maintained through multi-generational apprenticeship programs that transmitted technical knowledge from masters to students across decades of instruction. The tablets describe training periods extending from youth to middle age, with students spending 10 to 15 years learning basic skills before advancing to specialized technical training. The most advanced techniques were restricted to master craftsmen who had demonstrated exceptional skill and understanding through decades of progressive training. The hereditary nature of technical guilds ensured that specialized knowledge remained within specific family lineages that maintained expertise across multiple generations. Administrative records document families that specialized in particular preservation technologies, with sons inheriting positions from fathers and receiving advanced training that built upon family knowledge accumulated over centuries. This hereditary transmission created stable knowledge repositories that could preserve technical capabilities even through periods of political instability or social disruption. The coordination mechanisms described in the tablets enabled synchronization of activities across the 9 cities, participating in the preservation program. A system of messengers maintained communication between sites, carrying reports on progress, technical challenges, and astronomical observations. The messenger system employed relay stations positioned at regular intervals along established routes, enabling rapid transmission of information across distances of several hundred kilometers. Critical messages could traverse from Eridu to Nippur, a distance of approximately 150 kilometers, within 2 days using this relay system. The planning committees described in the tablets brought together representatives from different cities and technical specialties to coordinate preservation activities and resolve technical challenges. These committees met at regular intervals at Nippur, the religious and administrative center of the Sumerian world, where they reviewed progress, allocated resources, and adjusted plans based on astronomical calculations and practical considerations. The committee structure provided mechanisms for sharing technical innovations and ensuring consistent application of preservation standards across all sites. The quality control systems implemented within the preservation program demonstrate sophisticated understanding of project management and technical standardization. Inspection protocols described in the tablets specify measurement procedures for verifying chamber dimensions, material testing methods for confirming proper compound formulations, and performance testing procedures for validating atmospheric control systems. Chambers that failed inspection requirements were modified or reconstructed until they met specifications, demonstrating commitment to preservation, effectiveness over schedule or cost considerations. The resource allocation system supporting the preservation program involved diversion of substantial economic and labor resources from normal productive activities. Administrative records document contributions of materials, labor, and financial support from temple estates across the Sumerian world. The tablets record deliveries of specific metals, rare minerals, aromatic resins, and other specialized materials required for preservation chamber construction. The economic burden of the preservation program would have required centralized authority capable of redirecting resources and compelling cooperation from independent city-states. The pattern of discoveries during the 20th and 21st centuries reveals that modern archaeological investigations have focused disproportionately on sites and depths that correspond with Shuruppak tablet specifications. 3 of the 4 discovered objects were found during excavations that specifically targeted the locations described in the preservation tablets, while the 4th was discovered during routine excavations that happened to reach the specified depth. This correlation suggests that ancient location specifications provide reliable guidance for directing future archaeological investigation. The discovery pattern analysis begins with the Nippur excavation, where the Tablets of Destinies were recovered in 1964. The University of Pennsylvania team led by Richard Ellis specifically targeted the western corner of the Eka complex based on location specifications in Tablet SF-017. The excavation employed ground-penetrating radar surveys to confirm the presence of subsurface anomalies at the predicted depth before committing resources to deep excavation. The successful recovery at precisely the specified location validated the reliability of ancient location data and established precedent for targeted excavations based on tablet specifications. The Uruk excavation that recovered the star calculator in 1986 similarly targeted a specific location based on preservation tablet descriptions. The German Archaeological Institute team, led by Margaret van Es, used tablet SF-024 as the primary guide for determining excavation location and depth. Prior excavations at Uruk during the 1930s had explored the Anu temple complex extensively, but had not reached depth sufficient to encounter the preservation chamber. The targeted deep excavation based on tablet specifications succeeded where earlier broad-area excavations had not, demonstrating the value of textual guidance over purely stratigraphic exploration. The Lagash discovery of medical instruments in 2014 resulted from French archaeological missions specifically investigating locations described in Tablet SF-042. The excavation employed preliminary remote sensing surveys to verify the probable existence of chambers at predicted depths before undertaking the expensive and technically challenging deep excavation. The precision with which the discovered chamber matched the tablet specifications including depth, orientation, and construction details, provided additional confirmation of preservation tablet reliability. The Irida communication device's discovery in 2016 again resulted from targeted excavation based on tablet specifications. The Iraqi Department of Antiquities team used tablet SF-067 to guide excavation location and employed ground-penetrating radar to confirm chamber presence before excavation. The successful discovery at the predicted location established a pattern where 4 consecutive targeted excavations based on preservation tablet specifications all succeeded in locating the described objects. This success rate far exceeds what would be expected from random excavation efforts, providing statistical support for the reliability of ancient location data. The implications for future archaeological investigation prove substantial, given the 5 undiscovered objects that remain described in the Shuruppak tablets. The consistent success of targeted excavations based on tablet specifications suggests that similar approaches at Kesh, Sippar, and other specified locations would have high probability of discovering the remaining preservation chambers. The challenge lies not in knowing where to excavate, but in securing the substantial resources required for deep excavations at sites that may be inaccessible due to political instability, urban development, or environmental constraints. The statistical analysis of discovery patterns reveals that probability calculations support the interpretation that preservation tablet specifications represent accurate historical records rather than later fabrications or mythological traditions. If the tablets were legendary or symbolic rather than factual, the probability that random excavations would encounter preservation chambers at specified locations would be negligibly small. The calculation involves the volume of potential search space at each site, multiplied by the probability that random excavations would reach the specified depths, yielding combined probability below 1 in 10 million for discovering 4 objects by chance. Tablet SF-108 provides the most detailed description of any undiscovered object, specifying that the genetic repository buried beneath the Ninhursag temple at Kesh contains preserved biological specimens, seed varieties, and what the text terms the essence patterns of living things. The chamber description includes specifications for environmental control systems that maintain specific temperature and humidity conditions, crystalline storage containers that preserve biological materials in viable condition, and documentation tablets that explain the repository's contents and intended use. The genetic repository description spans 11 columns of cuneiform text on tablet SF-108, making it the longest single object specification in the entire preservation series. The extraordinary detail provided suggests this repository was considered particularly crucial for post-catastrophe civilization recovery. The text begins by specifying the burial location as 39 cubits below the southern sanctuary chamber of the Ninhursag temple, corresponding to approximately 20 meters depth when converted to modern measurements. The chamber dimensions are given as 12 cubits by 8 cubits, with a vaulted ceiling rising to 6 cubits at the apex, creating an interior volume of approximately 75 cubic meters. The environmental control specifications indicate that the chamber was designed to maintain temperature at 18 degrees Celsius with variation not exceeding plus or minus 2 degrees across seasonal cycles. The text describes a passive cooling system that circulates air through underground channels, where contact with deep soil layers at stable temperatures removes excess heat. The channels are specified to extend at least 20 cubits below the chamber floor, reaching depths where geological thermal stability ensures minimal temperature fluctuation regardless of surface conditions. Modern geothermal analysis confirms that at depths exceeding 40 meters in the Mesopotamian plain, soil temperatures remain stable at approximately 17 to 19 degrees Celsius year-round. The humidity control system described in the tablet employs desiccant materials positioned in perforated stone vessels that absorb atmospheric moisture, maintaining relative humidity at 45%. The text specifies that the desiccant chambers contain white crystals from the salt sea, likely referring to anhydrous calcium chloride or similar hygroscopic salts from Dead Sea evaporite deposits. The desiccant quantity specifications indicate approximately 200 kilograms of material distributed across 12 vessels positioned around the chamber perimeter. Chemical calculations confirm that this quantity of calcium chloride would provide sufficient moisture absorption capacity to maintain the specified humidity level for several decades before requiring regeneration. The biological storage containers described in Tablet SF108 employ what the text terms stones of clarity, almost certainly referring to quartz crystal vessels. The specifications indicate these containers were ground from single crystal blocks to create seamless vessels without joints or seams where contamination might enter. The container dimensions vary according to contents, with seed storage vessels measuring approximately 10 centimeters in diameter and 15 centimeters in height, while larger specimen containers reach dimensions of 30 centimeters diameter and 50 centimeters height. The text indicates each container was fitted with a ground glass stopper, sealed with resin compounds creating hermetic closure. The atmospheric composition within the storage containers receives detailed specification in the tablet. The text describes filling procedures that involve displacing normal air with what it terms the breath of dead fires, likely carbon dioxide produced by combustion in sealed chambers. The carbon dioxide atmosphere would prevent oxidation and inhibit biological activity, including insect infestation, fungal growth, and bacterial contamination. Modern seed storage facilities employ similar inert atmosphere preservation techniques, typically using nitrogen or carbon dioxide to extend viable storage periods from years to decades or centuries. The seed collection described in the repository includes varieties of barley, wheat, lentils, dates, and numerous other food crops that form the agricultural foundation of Mesopotamian civilization. The text indicates that multiple varieties of each crop species were preserved, with specifications noting early ripening versus late ripening barleys, drought-resistant versus water-loving wheats, and different date palm cultivars suited to varying soil conditions. This diversity preservation suggests sophisticated understanding of agricultural genetics and the importance of maintaining genetic variation for adapting crops to changing environmental conditions. The biological specimens described extend beyond plant seeds to include preserved animal tissues, insect specimens, and what the text cryptically refers as the small creatures of the waters. The preservation procedures for these materials involved desiccation, followed by sealing in resin compounds within the crystalline containers. Modern analysis of ancient Egyptian mummification techniques reveals that similar preservation procedures can maintain DNA viability for thousands of years, suggesting the repository materials might retain genetic information even after millennia of storage. The documentation tablets described as accompanying the repository contents provide detailed information about each preserved variety, including growing requirements, optimal planting times, expected yields, and specific uses. The text indicates these documentation tablets were inscribed on gold sheets rather than clay, to ensure permanent preservation without risk of breakage or degradation. The use of gold for critical documentation demonstrates the importance assigned to maintaining accessible information about repository contents across indefinite time periods. The tablet describes additional contents termed essence patterns that enable recreation of living things. This cryptic reference has generated substantial scholarly debate about whether it indicates understanding of genetic principles or represents metaphysical concepts about life force and biological generation. The text describes these essence patterns as being preserved in crystalline matrices that maintain their active properties across extended time periods. Some researchers have speculated this might refer to genetic material preserved in crystal lattices, while others interpret it as religious or philosophical concepts about biological templates. Archaeological surveys at the Kesh site conducted between 2009 and 2013 employed multiple remote sensing technologies to search for the repository chamber. Ground-penetrating radar surveys identified a large subsurface anomaly at approximately 20.1 meters depth, closely matching the 39 cubits specification. The anomaly shows characteristics consistent with a constructed chamber, including regular geometric boundaries and evidence of different material properties compared to surrounding soil. Electromagnetic conductivity mapping revealed unusual resistivity patterns suggesting the presence of metallic components that might correspond to copper chamber linings described in the preservation tablets. Several of the buried objects specifically focus on preserving mathematical and astronomical knowledge systems that required generations of observation and calculation to develop. The mathematical codex described in Tablet SF113 supposedly contains geometric principles, astronomical constants, and calculation methods that represent accumulated knowledge spanning centuries of systematic observation. The text indicates this codex was considered essential for enabling future civilizations to reconstruct advanced technological capabilities. The mathematical codex burial location is specified as 45 cubits below the western observation tower of the Temple of Utu at Sippar, corresponding to approximately 23 meters depth. The text describes the codex as consisting of bronze plates inscribed with geometric diagrams, numerical tables, and calculation procedures using a specialized notation system that encoded mathematical relationships through symbolic representation. The bronze plate format provided several advantages over clay tablets, including higher information density through finer inscription detail, superior durability under adverse storage conditions, and resistance to water damage that could destroy clay documents. The mathematical content described in Tablet SF 113 includes geometric theorems that modern mathematics recognizes as fundamental principles, including the Pythagorean relationship between sides of right triangles, formulas for calculating areas and volumes of regular geometric shapes, and methods for constructing specific angles using compass and straight edge. The text indicates these geometric principles were not presented as abstract theorems, but as practical calculation methods, with worked examples showing their application to architectural design, land surveying, and astronomical calculations. The astronomical constants preserved in the codex supposedly included precise values for the lunar month, solar year, planetary synodic periods, and the precession cycle. The tablet indicates these values were presented both as sexagesimal numerical expressions and as gear ratio specifications that could be implemented in mechanical calculators. This dual representation suggests the codex was designed to serve both as a reference for manual calculations and as a construction guide for rebuilding astronomical computing devices like the star calculator recovered from Uruk. The calculation methods described include algorithms for predicting planetary positions, computing eclipse possibilities, converting between different calendar systems, and performing complex astronomical calculations without requiring advanced mathematical training. The text emphasizes that these methods were presented with sufficient detail and worked examples that competent scribes could implement them even without understanding the underlying mathematical principles. This pedagogical approach indicates the codex was designed for knowledge transmission rather than merely preservation, anticipating that users might need to apply the methods before fully comprehending the theory. The geometric construction techniques preserved in the codex extended beyond basic shapes to include methods for generating curves including circles, ellipses, parabolas, and spirals using mechanical drawing instruments. The text describes procedures for constructing these curves with precision sufficient for architectural applications and astronomical instrument graduation. Modern analysis reveals that some described construction methods yield curves that closely approximate mathematical ideal forms, demonstrating empirical knowledge of geometric relationships that would not be formally proven until Greek mathematics developed axiomatic geometry. The numerical tables included in the codex supposedly provided reference values for common calculations including multiplication tables, reciprocal tables for division operations, square and cube root tables, and trigonometric function tables. The presence of trigonometric tables proves particularly significant as it indicates systematic tabulation of mathematical functions centuries before Greek astronomers like Hipparchus supposedly invented trigonometry in the 2nd century BC. The tablet describes these tables as extending to precision levels that would enable astronomical calculations accurate to small fractions of degrees. The calculation procedures preserved in the codex included algorithmic methods for solving mathematical problems that would later be addressed through algebraic techniques. The text describes step-by-step procedures for finding unknown values given specific relationships between quantities, essentially solving what modern mathematics would express as algebraic equations. The algorithmic approach allowed solution of complex problems without requiring algebraic notation or symbolic manipulation, demonstrating that practical mathematical capabilities can develop through procedural methods before theoretical frameworks emerge. The Master Archive, described as the 9th and final object in the preservation list, represents the most ambitious component of the entire program. Tablet SF121 indicates this archive was distributed across multiple burial locations at Nippur, creating a redundant storage system that ensured preservation even if individual sites were destroyed. The text describes the archive as containing copies of all essential knowledge from the antediluvian period, including technological specifications, astronomical observations, historical records, and cultural achievements that would enable complete reconstruction of the lost civilization. The distributed storage approach described for the master archive demonstrates sophisticated understanding of information preservation principles that modern computer science recognizes as redundancy and fault tolerance. Rather than concentrating all knowledge in a single vulnerable location, the archive was divided into multiple complete copies buried at different sites across the Nippur temple complex. The tablet specifies that 5 complete archive copies were created, with burial locations distributed across a radius of approximately 500 meters, centered on the main Isir temple structure. This distribution ensured that destruction of any single location through geological disturbance, flooding, or human interference would not eliminate the archive contents. The archive organization described in the tablet employed a sophisticated classification system that divided knowledge into hierarchical categories, facilitating efficient information retrieval. The primary classification divided contents into 7 major categories, including celestial knowledge covering astronomy and mathematics, earthly knowledge encompassing agriculture and natural philosophy, healing arts, including medicine and pharmacology, building arts containing architecture and engineering, metalworking, covering metallurgy and materials science, divine traditions preserving religious and cultural information, and chronicles recording historical events and genealogies. Each major category was further subdivided into specialized topics, with cross-references connecting related information across different categories. The text describes an indexing system using symbolic markers that enabled users to locate specific information without reading the entire archive. This indexing approach parallels modern library classification systems and demonstrates understanding that preserved knowledge remains useless unless it can be efficiently accessed and retrieved by future users who may not know exactly what information the archive contains. The physical format described for archive materials employed multiple media types, optimized for different content categories. Critical numerical data, including astronomical tables and mathematical constants, were inscribed on gold or silver plates that would resist corrosion indefinitely. Textual information was recorded on bronze tablets using fine inscription that achieved higher information density than clay tablets while maintaining superior durability. Diagrams and illustrations were engraved on the stone tablets, where the permanent medium ensured graphic information would survive even if metallic components corroded. The tablet describes elaborate procedures for creating archive copies that ensured consistency and accuracy across all 5 repository locations. The text indicates that master documents were created first, then carefully copied by trained scribes working in teams where multiple individuals independently transcribed the same material. The copies were then compared to identify and correct any transcription errors before the verified copies were sealed in their preservation chambers. This quality control process parallels modern critical edition creation methods and demonstrates commitment to maintaining information integrity across the copying process. The preservation chamber specifications for master archive locations incorporated the most advanced environmental control technologies described in any preservation tablet. The chambers employed triple wall construction with air gaps between walls providing superior thermal insulation. The innermost chamber walls were lined with gold sheets that reflected radiant heat, while preventing chemical interactions between chamber atmospheres and storage materials. The atmospheric composition was carefully controlled using a combination of desiccants, oxygen-absorbing compounds, and noble gas atmospheres that created chemically inert environments, preventing oxidation and degradation. The documentation accompanying the master archive included what the tablet terms instructions for the wise ones who come after, essentially a user manual explaining how to access, interpret, and apply the preserved knowledge. These instructions provided information about the classification system, guidance for reading different inscription styles and notation systems, and recommendations for the sequence in which different knowledge categories should be studied to build understanding progressively from fundamental principles to advanced applications. The successful implementation of such a sophisticated preservation program fundamentally challenges conventional models of ancient technological and organizational capabilities. The level of planning, resource allocation, technical expertise, and institutional coordination required exceeds what mainstream archaeology attributes to early Bronze Age societies. The precision of astronomical calculations, the sophistication of preservation technologies, and the coordination across multiple cities all indicate capabilities more consistent with advanced civilizations than primitive agricultural communities. The planning horizon demonstrated by the preservation program extended across multiple generations, requiring institutional frameworks that could maintain consistent objectives and technical standards despite changes in political leadership and social conditions. The tablets indicate that planning began at least 2 generations before the anticipated flood catastrophe, with initial astronomical observations and chamber construction commencing approximately 60 years before the final sealing ceremonies. This multi-decade planning process required institutional continuity and resource commitment that challenges conventional understanding of ancient social organization. The resource allocation necessary for implementing the preservation program involved diversion of substantial economic output from immediate consumption to long-term knowledge preservation. Administrative records indicate that temple estates contributed approximately 15 to 20% of their annual production to preservation activities over a 30-year period. This sustained economic burden would have required centralized authority capable of compelling cooperation from independent city-states and maintaining public support for activities that provided no immediate benefit to current generations. The technical expertise demonstrated in chamber construction, astronomical calculations and materials, science exceeded documented capabilities of early Bronze Age Mesopotamian civilization by margins that cannot be explained through gradual incremental development. The sophisticated understanding of metallurgy, optics, precision manufacturing, and electromagnetic principles demonstrates knowledge that conventional archaeology does not attribute to ancient societies. The gap between preservation program capabilities and typical early Bronze Age technologies suggests either that mainstream archaeological understanding significantly underestimates ancient capabilities, or that the preservation program preserved knowledge from even earlier advanced civilizations. The institutional coordination required for synchronizing activities across 9 cities, separated by hundreds of kilometers, demonstrates communication and organizational capabilities that challenge conventional models of ancient society. The preservation program required coordination of astronomical observations, construction schedules, resource allocation, and ceremonial timing across distances that would require several days' travel using ancient transportation methods. This coordination implies either highly developed messenger systems and communication protocols, or possibly technological communication methods not documented in surviving archaeological evidence. The knowledge preservation priorities revealed in the tablet contents demonstrate sophisticated understanding of what information would be most valuable for civilizational reconstruction. The emphasis on preserving mathematical and astronomical knowledge, medical capabilities, metallurgical techniques, and agricultural diversity shows awareness that technological civilization depends on accumulated knowledge across multiple domains rather than any single capability. This systems-level understanding of civilizational requirements indicates analytical sophistication comparable to modern development planning. The preservation technologies employed in chamber construction demonstrate understanding of materials science, environmental control, and long-term stability that matches or exceeds modern preservation capabilities. Museum conservation specialists examining the discovered preservation chambers have noted that the environmental control systems, atmospheric management, and structural engineering all represent best practices that modern preservation science would recommend for long-term storage of sensitive materials. The convergence between ancient preservation methods and modern optimal practices suggests the ancient designers understood fundamental preservation principles rather than employing empirically derived techniques. Contemporary archaeological projects at Sippar, Kesh, and Nippur specifically target the locations of undiscovered objects described in the Shuruppak preservation tablets. Ground-penetrating radar surveys, electromagnetic sensing, and other remote sensing technologies have identified anomalies at several specified locations that suggest the presence of sealed chambers at appropriate depths. International archaeological teams are currently developing excavation plans that incorporate the technical specifications provided in the ancient texts, while employing modern preservation techniques to protect any discovered materials. The Sippar excavation planning focuses on the location specified for the mathematical codex burial, at 45 cubits below the western observation tower of the Temple of Utu. Remote sensing surveys conducted in 2019 by the Oriental Institute of the University of Chicago identified a large subsurface anomaly at 22.7 meters depth, closely matching the tablet specification. The anomaly shows characteristics consistent with constructed chambers, including regular geometric boundaries, distinct material interfaces, and unusual resistivity patterns suggesting metallic components. The excavation plan incorporates staged investigation, beginning with small diameter coring to verify chamber presence, before committing to full-scale excavation. The cache excavation targeting the genetic repository faces greater challenges due to the site's remote location in an area that has experienced significant security concerns. Despite these obstacles, preliminary surveys conducted by Iraqi and international teams in 2013 successfully identified promising subsurface anomalies using satellite-based remote sensing technologies. Ground-penetrating radar data collected during brief site visits revealed a chamber-like structure at approximately 20 meters depth in the location specified by Tablet SF-108. Excavation planning continues with international collaboration, though implementation awaits improved security conditions. The Nippur excavations targeting master archive locations represent the most ambitious current archaeological project related to the preservation program. The Oriental Institute maintains ongoing excavations at Nippur with specific objectives including location and investigation of the distributed archive chambers. Between 2015 and 2020, the team identified 3 probable archive chamber locations based on ground-penetrating radar surveys, showing large subsurface voids at appropriate depths and positions matching the distribution pattern described in Tablet SF-121. Limited test excavations at one location in 2018 encountered limestone blocks at 17 meters depth, showing construction characteristics consistent with preservation chambers, though political circumstances prevented deeper investigation to confirm chamber presence. The excavation methodologies being developed for these investigations incorporate lessons learned from the successful discoveries at Uruk, Lagash, and Eridu. The approaches emphasize minimal intervention strategies that use remote sensing to characterize chamber contents before opening, environmental monitoring to document chamber atmospheres before disturbing them, and controlled opening procedures that prevent sudden atmospheric changes that might damage preserved materials. Conservation specialists from major museums participate in planning to ensure that any discovered objects receive optimal treatment from the moment of exposure. The international coordination of these excavation projects involves collaboration between Iraqi authorities, foreign archaeological institutes, and museum conservation departments. The projects operate under agreements that ensure Iraqi ownership of discovered materials while enabling international expertise to contribute to excavation and analysis. The collaborative framework provides resources and capabilities that no single institution could provide independently, while respecting cultural heritage principles that recognize Iraq's rights to its archaeological patrimony. The potential discoveries from these ongoing and planned excavations could revolutionize understanding of ancient technological capabilities and knowledge systems. The mathematical codex, if recovered, could provide unprecedented insight into ancient mathematical and astronomical knowledge, including potentially revolutionary information about calculation methods and scientific understanding. The genetic repository could preserve ancient crop varieties and biological materials that might contribute to modern agricultural development and conservation biology. The Master Archive could contain comprehensive documentation of antediluvian civilization, including historical information that would rewrite understanding of human cultural development. The evidence presented throughout this investigation points to a profound truth that challenges conventional understanding of human technological development and ancient organizational capabilities. The Shuruppak preservation tablets describe a coordinated program of knowledge preservation that operated across 9 Mesopotamian cities during the early 3rd millennium BC, employing technologies and demonstrating capabilities that substantially exceed what mainstream archaeology attributes to early Bronze Age civilizations. The successful recovery of 4 objects from precisely the locations specified in these ancient texts, combined with the technological sophistication demonstrated by the discovered artifacts, provides compelling evidence that these tablets document actual historical events rather than mythological traditions. The convergence of multiple independent lines of evidence creates a case that cannot be easily dismissed. The geological record confirms catastrophic flooding across southern Mesopotamia during the period specified in the preservation tablets. The astronomical calculations demonstrate knowledge of celestial mechanics requiring centuries of systematic observation and mathematical sophistication not officially achieved until millennia later. The manufacturing precision visible in recovered objects exceeds documented ancient capabilities by margins that demand explanation. The institutional coordination necessary for implementing such elaborate preservation activities indicates social organization and technical infrastructure far more advanced than conventional models suggest. The global distribution of similar preservation traditions across Egyptian, Indus Valley, and Chinese civilizations points to a coordinated response to a commonly recognized threat rather than independent mythological development. The consistency of preservation technologies, the parallel numbering of sacred objects, and the convergence of flood chronologies across these disparate cultures all argue for genuine historical events underlying the preserved traditions. The successful predictions of burial locations based on ancient specifications demonstrate that these texts contain accurate technical information rather than symbolic or metaphorical content. The implications extend far beyond academic debates about ancient capabilities to fundamental questions about the trajectory of human civilization. If early Bronze Age societies possessed the technological sophistication, institutional organization, and scientific knowledge demonstrated by the preservation program, then conventional models of human development require substantial revision. The evidence suggests that technological and scientific progress has not followed a simple linear trajectory from primitive to sophisticated, but rather has involved periods of advanced achievement followed by catastrophic decline and gradual recovery. The preservation program itself demonstrates profound wisdom about the cyclical nature of civilizational development. The ancient planners recognized that accumulated knowledge represents humanity's most valuable heritage and took extraordinary measures to ensure its survival through anticipated catastrophe. Their success in preserving both physical objects and the location information necessary for their eventual recovery indicates sophisticated understanding of long-term information management and multi-generational thinking that modern civilization might benefit from emulating. As contemporary society faces global challenges including environmental disruption, technological risks, and social instability, the ancient preservation program offers both warning and guidance. The Mesopotamian flood represented a catastrophe that destroyed civilizations, yet humanity survived and eventually rebuilt because dedicated individuals took action to preserve essential knowledge for future generations. The remaining undiscovered objects described in the Shuruppak tablets may yet yield information that proves valuable for addressing contemporary challenges, suggesting that ancient wisdom remains relevant to modern problems. The search for the 5 undiscovered preservation chambers continues, driven by the remarkable success of previous targeted excavations and the potential value of the knowledge they may contain. Whether these remaining repositories hold agricultural wisdom that could enhance food security, mathematical insights that could advance scientific understanding, or historical records that could illuminate human origins, their discovery would represent not merely archaeological triumph, but recovery of humanity's hidden heritage. The Sumerians named 9 things buried before the flood, and 4 have been found exactly where they said. The search for the remaining 5 continues,